Ladies and gentlemen, welcome to the most ambitious journey humanity has ever dreamed of. A journey not to Mars, not to the Moon, but to Venus, the most misunderstood and enigmatic planet in our solar system. Venus, often called Earth's twin, is shrouded in mysteries, its thick clouds hiding a world of extremes. But hidden within those clouds lies an incredible opportunity, a frontier waiting to be explored. Today we're embarking on a deep dive into what it would take to make Venus our second home. From cutting-edge technologies to floating cities, from taming its harsh environment to unlocking its hidden resources, this is your complete guide to colonizing Venus. Why Venus, you might ask? With its dense atmosphere and gravity similar to Earth's, Venus offers unique advantages for long-term human settlement. And unlike Mars, the potential for habitable conditions exists at a specific altitude, floating above the planet's inhospitable surface. But let's be clear, this isn't a story of convenience. Venus presents challenges that test the limits of human ingenuity. Temperatures hotter than an oven, atmospheric pressure that could crush a submarine, and clouds laced with sulfuric acid. Yet, with every challenge comes innovation. Imagine cities suspended high above the clouds, thriving with life, powered by the sun, and self-sufficient in resources. A vision that once seemed like science fiction is now within the realm of possibility. To achieve this, we'll need to rewrite the playbook of space exploration. New materials, advanced robotics, and sustainable energy systems will become the foundation of our Venusian dream. But colonizing Venus is not just about technology. It's about human resilience. It's about solving problems, uniting nations, and pushing the boundaries of what we thought was possible. So join us as we explore the journey to Venus. From the science of its atmosphere to the engineering marvels required, we'll uncover every detail of what it takes to make this vision a reality. This is not just a guide. It's a call to imagine, to innovate, and to pioneer the next chapter of humanity's story. Let's begin. Venus's atmosphere is a dense and dynamic system, unlike anything we've encountered on Earth. Composed primarily of carbon dioxide, it creates a runaway greenhouse effect, trapping heat and driving surface temperatures to extremes. This heavy carbon dioxide blanket makes up over 96% of the planet's atmosphere, with nitrogen accounting for much of the remaining 4%. Trace amounts of other gases, such as sulfur dioxide, contribute to the unique and hostile conditions. What sets Venus apart is the sheer density of its atmosphere, which is about 90 times heavier than Earth's. At its surface, the pressure is equivalent to being nearly a kilometer underwater, crushing and relentless. High above the surface, thick clouds of sulfuric acid swirl in chaotic patterns, reflecting sunlight and creating the planet's bright, iconic appearance. These clouds dominate the upper atmosphere, where they play a critical role in the planet's energy balance. Sulfuric acid droplets not only shape Venus's weather, but also form a reflective layer that bounces much of the sun's energy back into space. This phenomenon keeps Venus hotter than Mercury, despite being farther from the sun. The dynamic winds in the upper atmosphere move at astonishing speeds, circling the planet in just 4 Earth days. These super-rotating winds create turbulence and transport heat across the globe, driving Venus's extreme climate. The lower atmosphere, however, is far more stagnant, with slow-moving winds and a dense, oppressive haze. Here, temperatures climb to nearly 475 degrees Celsius, making survival without protective technology impossible. Oxygen, so vital to life on Earth, is almost non-existent on Venus. Instead, the air is saturated with carbon dioxide, creating conditions uninhabitable for humans without advanced life support systems. Despite these extremes, the thick atmosphere provides an opportunity for exploration and settlement at certain altitudes. About 50 to 60 kilometers above the surface, the temperature and pressure become much more Earth-like, presenting a potential zone for human habitation. Understanding the composition of Venus's atmosphere is key to designing systems that can thrive within it. From harvesting gases for energy to developing materials that resist corrosion, every aspect of colonization depends on this knowledge. By studying Venus's atmosphere, scientists can also uncover clues about the planet's history. What caused its climate to become so extreme? And could these lessons help us better understand the future of Earth's environment? The mysteries hidden within Venus's atmosphere are both a challenge and an invitation. To colonize Venus, we must first unravel the secrets of the air we'll one day call home. Venus is home to some of the most extreme conditions in the solar system, with temperatures on its surface hot enough to melt lead. These blistering temperatures, reaching an average of 475 degrees Celsius, are maintained by the planet's thick carbon dioxide atmosphere and runaway greenhouse effect. The heat is unrelenting, as Venus's slow rotation and lack of significant tilt mean that there are no seasons. Day and night blend together in an eternal furnace, with temperatures remaining consistent across the planet. Pressure on Venus is equally unforgiving, crushingly dense compared to Earth. At ground level, the pressure is approximately 92 times that of sea level on Earth, comparable to the conditions found deep in the oceans. This immense pressure presents one of the biggest hurdles for any mission to Venus's surface. Standard spacecraft or probes must be specially designed to withstand the crushing forces for even a short duration. Interestingly, the pressure eases as you rise through the atmosphere. At around 50 kilometers above the surface, conditions become much more Earth-like, with pressure comparable to what we experience at sea level. This creates a unique potential for human habitats to float within this altitude range, avoiding the deadly conditions below. However, any structure or system must still contend with the ever-present threat of heat and corrosive clouds. The surface of Venus, by contrast, is almost entirely inaccessible with current technology. Any equipment attempting to land must endure both the intense heat and the crushing weight of the atmosphere, a feat achieved by only a handful of probes. Even robustly designed landers like the Soviet Venera missions survived for only a matter of hours before succumbing to the extreme environment. These conditions demand constant innovation for future exploration and research. High above the surface, the heat diminishes significantly, but the atmosphere remains a volatile mix of winds and sulfuric acid clouds. Any attempt to navigate these layers will require materials capable of withstanding corrosive and abrasive forces. Despite these challenges, the consistent pressure gradient throughout Venus's atmosphere offers opportunities. It allows for the deployment of systems like balloons or airships that can be used for research, transport, and even habitation. Understanding how temperature and pressure interact across Venus's atmospheric layers is crucial. It not only shapes the design of our technologies, but also dictates where humans can feasibly exist within this alien world. The extremes of Venus may seem insurmountable, but within these very conditions lie the keys to unlocking its mysteries. Each challenge, from heat to pressure, fuels our determination to turn this vision into reality. High above the surface of Venus lies a vast and complex layer of clouds, stretching from roughly 45 to 70 kilometers in altitude. These clouds are made primarily of sulfuric acid, suspended in a dense mix of carbon dioxide and trace gases. The cloud layer is thick and reflective, bouncing about 75% of incoming sunlight back into space. This creates Venus's brilliant, bright appearance when viewed from Earth, earning it the nickname Morning Star. These clouds are not uniform. They form distinct layers with varying properties. The lower layers are denser and hotter, while the upper layers are cooler and more dynamic, constantly shaped by strong winds. Super-rotating winds drive these clouds at incredible speeds, moving faster than the planet itself rotates. This phenomenon causes the entire cloud system to circle Venus in just 4 Earth days, a stark contrast to its slow rotation. The acidic nature of the clouds presents a unique challenge for any exploration or colonization effort. Materials must be carefully chosen to resist corrosion from prolonged exposure to sulfuric acid droplets. Within the cloud layer, temperatures are significantly cooler than on the surface, making it a potential zone for human habitation. At certain altitudes, the environment is surprisingly stable, with temperatures similar to those on Earth. These layers also contain trace amounts of water vapor, an intriguing factor for scientists studying the potential for life. Though conditions remain harsh, some speculate that microbial life could exist in the less extreme portions of the clouds. Despite their beauty from a distance, these clouds block almost all visible light from reaching the surface of Venus. The result is a dim, eerie landscape below, perpetually shrouded in shadow. In addition to their visual effects, the clouds play a significant role in regulating Venus's climate. They trap heat effectively, contributing to the intense greenhouse effect that defines the planet's environment. Understanding the dynamics of these clouds is critical for designing floating habitats or exploration systems. Their turbulence, combined with high-altitude winds, poses both risks and opportunities for aerial technologies. Studying these clouds also offers insights into the history of Venus's atmosphere. By analyzing their composition and movement, we can uncover clues about how the planet's climate evolved into its current state. The cloud layers of Venus are both a barrier and a beacon. They challenge our ingenuity while holding the promise of discovery, inspiring us to push further into the unknown. The weather on Venus is as dynamic as it is extreme, dominated by fast-moving winds that sweep through the atmosphere at astonishing speeds. These super-rotating winds can reach up to 360 kilometers per hour, far outpacing the planet's slow rotation. This rapid movement creates a constant churning in the upper atmosphere, where winds circle the planet in just a few days. This phenomenon means that despite Venus's slow day-night cycle, the atmospheric motion ensures a more uniform distribution of heat. The winds are not uniform across all layers of the atmosphere. They are strongest in the upper cloud decks, where they propel sulfuric acid clouds around the globe. Closer to the surface, the winds slow dramatically, becoming nearly stagnant in comparison. This stark difference between upper and lower atmospheric motion creates a unique dynamic. The upper layers are turbulent and fast, while the dense lower atmosphere remains eerily still, trapping heat and pressure near the surface. Another fascinating aspect of Venus's weather is its lack of seasonal variation. With no significant axial tilt, the planet experiences relatively consistent conditions, with no dramatic shifts in weather patterns throughout the year. Lightning has also been detected within the atmosphere, a rare occurrence driven by the charged particles in the thick sulfur-rich clouds. Though less frequent than on Earth, these electrical storms add another layer of complexity to Venusian weather. At higher altitudes, the temperature drops, allowing for the formation of unique cloud structures. These clouds can appear streaked or wave-like, shaped by the powerful winds and turbulence in the atmosphere. Despite the high-speed winds, there is little in the way of rainfall. The sulfuric acid droplets that make up the clouds evaporate before reaching the surface, creating a perpetual cycle within the upper layers of the atmosphere. Occasionally, atmospheric waves are observed, rippling through the clouds and altering wind patterns. These waves are driven by the interaction of winds with the planet's topography and other atmospheric dynamics. Studying these weather patterns provides critical information for designing technologies that can survive and operate in such conditions. Understanding wind speeds and turbulence is vital for crafting stable floating habitats or deploying scientific instruments. The complexity of Venus's weather challenges us to rethink what we know about planetary climates. Each observation deepens our understanding of how winds, clouds, and heat interact on a world so unlike our own. Venus's weather is a story of extremes, from high-speed winds to unyielding heat. To thrive here, we'll need to master the planet's chaotic atmosphere and harness its forces for exploration and beyond. Living on Venus would require a complete reimagining of what human habitation means. The planet's extreme conditions make traditional surface settlements impossible, forcing us to look upward to its more hospitable upper atmosphere. At altitudes between 50 and 60 kilometers, temperature and pressure levels closely resemble those of Earth's surface. This habitable zone offers a rare opportunity for human survival, provided we can overcome the surrounding dangers. Floating habitats could become the cornerstone of Venusian colonization. These cities in the sky would need to be lightweight, resilient, and capable of supporting life in a dynamic and corrosive environment. Sulfuric acid clouds pose a major challenge for materials used in construction. Structures must be designed with advanced coatings or entirely new compounds to resist corrosion and degradation over time. Air quality will be another critical factor. Systems must constantly filter out harmful gases like carbon dioxide and sulfur compounds while maintaining breathable oxygen levels for the inhabitants. Energy generation will also need to be innovative and efficient. The proximity to the sun provides an abundant source of solar energy, but storage systems must be robust enough to handle the planet's chaotic weather patterns. Communication and navigation in Venus's atmosphere present further challenges. Dense clouds and high winds could interfere with signals, requiring novel solutions to maintain connectivity between habitats and Earth. Resource management will be key to long-term survival. Floating habitats must either import supplies from Earth or develop systems to extract resources directly from Venus's atmosphere, such as harvesting carbon dioxide for industrial processes. Psychological resilience will be as vital as technological innovation. Living in an isolated, enclosed environment, surrounded by hostile conditions, demands new approaches to maintaining mental health and community well-being. The potential for research and discovery is immense, with humans directly observing Venus's atmosphere from within. Scientists could study everything from atmospheric chemistry to potential signs of microbial life, contributing to our understanding of both Venus and Earth. Human habitation on Venus could also serve as a proving ground for off-world living. Lessons learned here could shape future colonization efforts across the solar system, providing a model for survival in even the harshest environments. Building a life above Venus is not just a technological challenge, it's a testament to human adaptability. It will require ingenuity, perseverance, and an unyielding commitment to exploring the unknown. The idea of floating habitats on Venus is born out of necessity. With surface conditions too hostile for any known life, the focus shifts to the more temperate regions of the planet's atmosphere. At an altitude of around 50 kilometers, the temperature and pressure are strikingly similar to those on Earth. This unique environment creates a narrow window where human life could potentially thrive. Floating habitats would take advantage of the dense carbon dioxide atmosphere, which provides natural buoyancy for structures filled with breathable air. Unlike on Earth, the very air we breathe becomes a lifting gas on Venus. These habitats offer a solution to Venus's most extreme challenges. By remaining above the scalding surface and the crushing atmospheric pressure, they bypass the worst of the planet's conditions. The consistent temperatures at these altitudes eliminate the need for extreme heating or cooling systems. Habitats would still face challenges, but they avoid the thermal extremes found lower in the atmosphere. Floating cities also present an opportunity to harvest resources directly from the atmosphere. Carbon dioxide, nitrogen, and trace amounts of other gases could be collected and processed for industrial and life support uses. Solar energy is plentiful at these heights, offering a clean and sustainable power source. The planet's proximity to the Sun ensures that habitats can harness consistent energy to power life support systems and research operations. Unlike surface colonies, floating habitats would be mobile. They could adjust their positions within the atmosphere, taking advantage of favorable winds or avoiding turbulent weather patterns. This mobility could also allow habitats to function as exploratory platforms. They could move across the planet to study its diverse atmospheric phenomena, uncovering new scientific insights. The design of these habitats would prioritize safety and redundancy. Advanced materials and engineering solutions would ensure resilience against the corrosive effects of sulfuric acid clouds and the high-speed winds. Floating habitats represent a scalable approach to Venus colonization. Small research stations could evolve into interconnected cities, creating a network of human presence above the clouds. This vision of floating habitats highlights human creativity in the face of adversity. It's a bold step that transforms Venus from an inhospitable world into a platform for exploration and possibility. In Venus's dense and multi-layered atmosphere, there exists a specific altitude range where conditions are surprisingly Earth-like. Between 50 and 60 kilometers above the surface, the temperature hovers around 20 to 30 degrees Celsius, making it one of the few places in the solar system outside Earth with such temperate conditions. At these altitudes, the atmospheric pressure is also manageable, roughly equivalent to what we experience at sea level on Earth. This balance of temperature and pressure creates a narrow but promising zone for human habitation. The air at this level is dense enough to provide buoyancy for floating habitats. Structures filled with breathable air could naturally remain aloft, leveraging the unique properties of Venus's atmosphere. While this altitude range offers better conditions than the surface, it is far from benign. Sulfuric acid clouds and high winds are persistent challenges, requiring habitats to be constructed from materials resistant to both corrosion and constant movement. Above this habitable zone, temperatures begin to drop sharply, and the air thins out, becoming less supportive of floating structures. This natural ceiling limits how high habitats can safely ascend. Below 50 kilometers, conditions rapidly deteriorate. Temperatures and pressures increase exponentially, pushing the limits of what any material or technology can endure for sustained periods. Within the habitable range, sunlight is still abundant, making it an ideal altitude for solar energy collection. This access to solar power ensures that floating habitats can maintain life support systems and other essential technologies. The winds at these altitudes, though fast, are relatively stable compared to lower atmospheric turbulence. This stability provides an opportunity for long-term stationary habitats or even mobile research platforms. The consistent conditions at this altitude reduce the need for complex environmental controls. While some systems will always be required to maintain breathable air and water, the temperate climate simplifies these challenges. The presence of trace gases like nitrogen and water vapor in this altitude range adds potential for resource extraction. These resources could support life support systems and industrial processes without constant resupply from Earth. This layer of the Venusian atmosphere offers not only a refuge from the planet's extremes, but also a platform for scientific exploration. It allows for direct study of Venus's atmospheric dynamics and surface conditions from a safe vantage point. By carefully designing habitats for this specific altitude, humanity can carve out a space in an otherwise inhospitable world. It is a delicate balance, but one that could unlock the potential of Venus as a new frontier. Designing structures to float in Venus's atmosphere requires a complete departure from traditional architectural concepts. These habitats must be lightweight, yet strong enough to withstand the harsh and corrosive environment. The key to their buoyancy lies in the dense Venusian atmosphere. Habitats filled with breathable air can act as floating vessels, leveraging the natural properties of the planet's thick carbon dioxide layer. Materials used for construction need to resist the constant presence of sulfuric acid in the clouds. Advanced composites or acid-resistant alloys will form the backbone of these floating cities, ensuring durability over time. The outer shell of the structures will serve as both a barrier and a resource. It will shield inhabitants from corrosive gases, while also acting as a platform for collecting solar energy and other environmental resources. To maximize efficiency, these habitats will likely feature modular designs. Interconnected pods or units will allow for flexibility, making it easier to expand, repair, or adapt the structures as needed. Aerodynamic shapes will also play a crucial role in stabilizing these floating habitats. Streamlined designs can reduce drag from the high-speed winds and ensure the structures remain steady at their designated altitudes. Inside, the design will prioritize comfort and sustainability. Compact living spaces, efficient use of resources, and closed-loop systems for water and air recycling will be integral to long-term habitation. Centralized hubs within the habitats can house essential systems like energy storage, life support, and communication arrays. These hubs will anchor the overall structure and distribute resources evenly to all living areas. The floating cities will also require extensive anchoring or positioning systems to remain stable within the winds. Tethering mechanisms or active stabilization technologies could help keep habitats in place or allow for controlled movement. For safety, redundancy will be built into every aspect of the design. Backup systems for power, air filtration, and structural integrity will ensure resilience against unexpected failures. The outer surfaces may also be equipped with systems to repel or neutralize sulfuric acid droplets. This could include advanced coatings or even active cleaning mechanisms to maintain the habitat's structural integrity. These floating structures will not just be shelters, but fully functional ecosystems. Designed to adapt to the Venusian environment, they will demonstrate humanity's ability to innovate and thrive in the most challenging conditions. Building habitats in Venus's atmosphere demands materials that can withstand a unique combination of challenges. These include intense winds, corrosive sulfuric acid clouds, and prolonged exposure to high temperatures. Lightweight but durable materials will be essential for maintaining buoyancy while ensuring the structural integrity of the habitats. Advanced composites like carbon fiber reinforced polymers could provide the necessary strength-to-weight ratio. Metals such as titanium and certain stainless steel alloys are promising candidates for their resistance to corrosion. These materials are already used in environments where exposure to acids and extreme conditions is common. Polymer-based coatings could further enhance the resistance of these metals and composites. These specialized coatings would protect against sulfuric acid, ensuring the longevity of external surfaces. Self-healing materials might also play a significant role. These innovative substances can repair minor damage automatically, reducing maintenance and improving the lifespan of structures in a harsh environment. For interior components, lightweight and flexible materials like aerogels could provide insulation. These materials would help regulate internal temperatures while adding minimal weight to the overall structure. Solar panels and other energy systems will require materials that perform efficiently in Venus's intense sunlight. Thin-film photovoltaics, known for their lightweight and flexible properties, could be an ideal choice. Transparent yet durable materials such as reinforced glass or acrylic will be necessary for windows or observation areas. These materials must provide clarity without compromising resistance to acid corrosion. The tethering and anchoring systems, if needed, would require materials capable of withstanding both constant tension and corrosive exposure. High-performance polymers or advanced metal alloys could meet these requirements. Inside the habitats, the focus will be on comfort and adaptability. Modular construction materials that can be easily reconfigured or repaired will allow the living spaces to evolve with the needs of their inhabitants. Recycling materials from Venus's atmosphere may also become a possibility. Extracting and processing carbon dioxide or sulfuric acid into usable compounds could reduce the reliance on supplies from Earth. The choice of materials will dictate the success and sustainability of these habitats. Every component must work in harmony with the environment, turning Venus's challenges into opportunities for innovation. Ensuring the long-term sustainability of floating cities on Venus will require closed-loop systems that minimize reliance on external supplies. These systems must recycle air, water, and waste to support a self-sufficient ecosystem. Energy production will be a cornerstone of sustainability. With abundant sunlight at these altitudes, solar energy can be harnessed and stored efficiently to power all life support and operational systems. Food production will need to take place within the habitats themselves. Hydroponic or aeroponic farming methods can grow crops in controlled environments, using minimal water and maximizing space. Extracting resources directly from Venus's atmosphere could provide essential materials for industry and life support. Carbon dioxide can be processed into oxygen for breathing, while sulfuric acid might be converted into useful compounds. Habitat materials will need to be repairable or replaceable using local resources. Recycling components and producing new materials on-site will reduce the dependence on costly resupply missions from Earth. Maintaining biodiversity within the habitats will be key to a balanced ecosystem. Microorganisms, plants, and even small animals could work together in a controlled biosphere to recycle nutrients and sustain life. Habitat stability in the face of atmospheric turbulence will require advanced adaptive technologies. Systems that can counteract high-speed winds or reposition the city within the atmosphere will be essential for long-term survival. Effective waste management will ensure nothing is lost in the closed-loop system. Organic waste can be composted for farming, while inorganic materials are processed for reuse or storage. Community health, both physical and psychological, will be critical in such an isolated environment. Habitats will need recreation areas, social spaces, and access to healthcare to ensure the well-being of their inhabitants. Expanding the habitats over time will require scalable designs. Starting with small research stations, these floating cities could gradually grow into larger, interconnected communities. Ongoing scientific research will help improve sustainability. Studying Venus's atmosphere and developing new technologies in situ will allow the cities to adapt more effectively to their environment. Sustainability isn't just about survival. It's about creating a thriving, resilient society. Floating cities on Venus will embody the principles of adaptability and innovation, paving the way for humanity's long-term presence on the planet. Venus's proximity to the Sun makes it an ideal candidate for solar energy generation. With nearly double the solar intensity of Earth, this abundant energy source could power entire floating cities. The thick cloud cover might seem like an obstacle, but at higher altitudes, significant sunlight still penetrates. Advanced solar panel technologies can harness this energy efficiently, even in less direct conditions. Thin-film solar panels, known for their lightweight and flexible properties, would be particularly suited for floating habitats. These panels could be integrated into the structure of the habitats themselves, maximizing energy collection. Energy storage systems will be just as important as the solar panels. Batteries or other storage technologies must hold enough power to sustain life support systems during periods of reduced sunlight. A key advantage of Venus's atmospheric environment is the lack of nighttime at certain altitudes. With continuous solar exposure, energy production could remain consistent, reducing the reliance on large-scale storage. In addition to traditional solar panels, Other technologies like solar concentrators could amplify energy capture. These systems focus sunlight onto smaller, highly efficient panels, generating more power in a compact space. The mobility of floating habitats offers another advantage for energy optimization. Habitats could be designed to reposition themselves within the atmosphere to maximize sunlight exposure throughout the day. Energy distribution networks within the habitats must be highly efficient. Wasted energy could strain life support systems, so every watt will need to be carefully managed and allocated. Solar-powered systems could also support secondary functions, such as atmospheric resource extraction. Energy-intensive processes like carbon dioxide conversion or water vapor harvesting would benefit from the abundant solar input. Maintaining the solar infrastructure in a corrosive environment will be a challenge. Panels and storage systems will require protective coatings or periodic maintenance to ensure longevity and performance. Excess energy could be stored or shared between interconnected habitats. A networked approach to energy management would create resilience, allowing floating cities to support each other during outages or periods of reduced efficiency. Harnessing solar energy on Venus represents more than just survival. It's the foundation for a thriving society. With the right technologies, this infinite resource can sustain not just a city, but a new frontier for humanity. Venus's atmosphere offers another untapped energy resource, its powerful winds. With speeds reaching up to 360 kilometers per hour in the upper atmosphere, these winds hold immense potential for energy generation. Floating habitats could integrate wind turbines or other energy-harnessing devices into their structures. These systems would convert the constant motion of the atmosphere into a steady supply of electricity. Unlike solar power, wind energy on Venus would remain consistent day and night. This reliability could serve as a critical backup during periods when solar generation might be less efficient. Turbine designs would need to account for the high-speed winds and corrosive environment. Lightweight, durable materials and advanced coatings would ensure these systems operate efficiently over long periods. Positioning turbines at various points on the habitat could capture energy from winds blowing in multiple directions. This decentralized approach would increase overall efficiency and reduce the risk of power interruptions. The dense atmosphere of Venus provides an additional advantage for wind energy. The higher air density means turbines can generate more power compared to similar systems on Earth. To prevent structural strain, wind energy systems must balance efficiency with stability. Advanced engineering will ensure that turbines do not compromise the habitat's buoyancy or overall integrity. Energy from the wind could also power resource extraction systems, such as devices that harvest carbon dioxide or other gases. These processes would benefit from the steady energy flow provided by the atmosphere's constant motion. Storage solutions will play a vital role in wind energy systems. Excess power generated during peak wind conditions could be stored for later use, ensuring a continuous energy supply for critical systems. Floating habitats might also use smaller modular turbines designed for easy replacement or repair. This adaptability would allow for ongoing upgrades as technology evolves and needs change. Wind energy could complement solar power, creating a hybrid energy network. By harnessing both sunlight and wind, floating cities would be better equipped to meet the demands of long-term habitation. The winds of Venus are more than a challenge. They're an opportunity. With the right technologies, this ceaseless force could become one of the pillars supporting life in the clouds. Beyond solar and wind, alternative energy solutions will play a crucial role in sustaining floating habitats on Venus. Diversifying energy sources ensures stability and resilience in such a challenging environment. One promising option is thermal energy. The significant temperature differences between Venus's upper atmosphere and its cooler cloud layers could be harnessed using thermoelectric systems, converting heat gradients into usable power. Chemical energy extraction is another potential avenue. The dense atmosphere, rich in carbon dioxide and trace gases, could fuel chemical reactors designed to produce electricity or generate useful compounds. Fuel cells could provide a compact and efficient backup power source. By utilizing hydrogen or other elements harvested from the atmosphere, these cells would offer reliable energy with minimal waste. Nuclear energy might also be considered for long-term stability. Small modular reactors could provide a constant energy supply, independent of atmospheric conditions, though they would require careful engineering to ensure safety. Kinetic energy from Venus's constant atmospheric motion could be harnessed in creative ways. Oscillating systems or vibration-powered generators might convert these forces into electricity, supplementing traditional turbines. Electrostatic energy created by the interaction of atmospheric particles is another frontier worth exploring. Systems designed to capture and convert these charged particles could create a novel source of power. Habitat mobility could also generate energy. Using the motion of floating cities within Venus's winds, regenerative systems could produce electricity while habitats navigate the atmosphere. Advanced energy storage solutions will enhance these systems. Flywheels or superconducting magnetic systems could store power efficiently, reducing losses and ensuring a steady supply during demand surges. Integrated hybrid systems would combine multiple energy sources into a unified network. By balancing solar, wind, and alternative methods, these systems would adapt dynamically to changing conditions. Energy harvesting technology might even extend to collecting energy directly from lightning within Venus's atmosphere. Though rare, these electrical discharges could provide high-intensity bursts of power if captured effectively. Exploring alternative energy solutions is not just about redundancy. It's about unlocking the full potential of Venus's unique environment. Each new approach brings humanity one step closer to thriving in the clouds. Energy storage will be the backbone of any sustainable habitat on Venus, ensuring a continuous power supply regardless of fluctuations in generation. Reliable storage systems are essential for balancing the needs of life support, research, and resource extraction. Battery technologies will likely be the primary solution for storing solar and wind energy. Advanced lithium-ion or solid-state batteries could offer high energy density, long lifespans, and the ability to operate in Venus's challenging conditions. Thermal energy storage is another promising approach. Excess energy could be used to heat a storage medium, such as molten salts or specialized ceramics, which would then release the heat to generate electricity as needed. Flywheel systems could provide a mechanical method of storing energy. By spinning a rotor at high speeds, these systems can store kinetic energy that can be converted back into electricity when required. Compressed gas storage offers another option. Energy can be used to compress gases into tanks, which can later release pressure to drive turbines and generate power, providing a flexible and scalable solution. Chemical storage solutions could take advantage of the resources available in Venus's atmosphere. Processes like splitting carbon dioxide into carbon monoxide and oxygen could create storable compounds with energy potential. Hydrogen storage systems may also play a role, especially if hydrogen can be extracted or synthesized on site. Stored hydrogen could fuel fuel cells, providing electricity with only water as a byproduct. Supercapacitors offer rapid charge and discharge capabilities, making them ideal for short-term storage and balancing power fluctuations. These systems could work alongside traditional batteries for maximum efficiency. Grid-scale energy storage might even be possible within interconnected habitats. By sharing stored energy across a network, floating cities can support each other during peak demand or generation shortfalls. Redundancy will be critical in all energy storage systems. Multiple methods of storage ensure that no single failure compromises the survival or functionality of the habitat. Regular maintenance and monitoring of storage systems will be required to ensure reliability. Automated diagnostics and repair technologies will likely be integral to keeping these systems operational in such a remote and harsh environment. Efficient energy storage transforms intermittent generation into a reliable and consistent power supply. It bridges the gap between potential and practical use, enabling life to flourish in Venus's skies. Balancing energy demand and supply on Venus will require highly adaptive systems capable of responding to changing conditions. Floating habitats must carefully match energy production with consumption to ensure uninterrupted operations. Dynamic energy management systems will play a central role. These systems will monitor real-time usage and generation, allocating power where it's needed most while preventing wastage. Peak energy demands will need to be addressed with storage solutions and reserve power sources. Batteries, flywheels, or hydrogen fuel cells can step in during spikes to maintain balance without overloading the grid. Demand-side management will also be crucial. Non-essential systems can be temporarily powered down during high-demand periods, ensuring that critical life support and safety functions always have priority. Habitat designs will incorporate energy-efficient technologies to minimize overall consumption. Advanced insulation, LED lighting, and optimized life support systems will reduce the energy burden significantly. Automation and artificial intelligence could optimize energy usage across all systems. AI algorithms will predict patterns, preemptively adjusting supply to avoid shortages or surpluses. Energy sharing between interconnected habitats can further stabilize the grid. Excess power generated by one city can be redirected to another experiencing a shortfall, creating a resilient energy network. Redundancy within energy systems will ensure there is no single point of failure. Multiple energy sources and backup systems will work in tandem, providing a layered safety net against unexpected disruptions. Resource-intensive activities such as atmospheric harvesting or industrial processes could be scheduled during times of surplus generation. This strategic timing will maximize energy efficiency and reduce strain on storage systems. Seasonal or environmental variations, while limited on Venus, may still influence energy dynamics. Systems must account for fluctuations in solar intensity or wind patterns to maintain consistent supply. Clear protocols will govern emergency energy situations. These protocols will prioritize life support and critical systems, redirecting all available resources to sustain human survival until normal operations resume. Balancing energy is not just a technical challenge, it's a vital part of making life possible in Venus's atmosphere. With precise planning and advanced technology, floating habitats can thrive on a carefully managed energy foundation. The initial entry into Venus's atmosphere is one of the most critical phases for any mission. The dense atmosphere creates immense aerodynamic forces, requiring robust heat shields to protect the craft during descent. As the spacecraft approaches the planet, it must endure extreme temperatures caused by atmospheric friction. Advanced ablative materials on the heat shield will dissipate this heat, safeguarding the interior systems. Deceleration is another challenge. The thick atmosphere creates intense drag, which can be used to slow the craft, but it also generates powerful mechanical stresses on the structure. Parachutes or inflatable braking systems could deploy in the upper atmosphere, further reducing speed. These systems must withstand turbulent winds and corrosive gases while maintaining stability. Entry vehicles will likely include modular designs to facilitate different stages of descent. Each module will separate at the right altitude, ensuring that only the essential components reach the desired level in the atmosphere. Autonomous navigation systems will play a vital role during entry. They will adapt to real-time conditions, adjusting trajectory and descent rate to account for wind speeds and atmospheric density. Communicating with Earth during this phase will be complex. The thick atmosphere and turbulent entry conditions could disrupt signals, requiring onboard systems to operate independently. Energy generation systems, such as solar panels, must remain protected during entry. Deploying these systems too early could risk damage, while waiting too long might delay power generation for essential functions. Temperature and pressure sensors on the entry vehicle will provide critical data during descent. This information will help ensure safe deployment of equipment and guide future missions based on real-time conditions. Once the craft stabilizes in the upper atmosphere, it will need to transition into a floating configuration. Inflatable balloons or other buoyant systems could deploy at this stage, allowing the habitat or probe to hover within the habitable zone. Redundancy in critical systems will be essential for success. Any failure in the heat shields, parachutes, or navigation could jeopardize the entire mission, making backups a non-negotiable requirement. Initial entry is more than a technical feat. It's the gateway to Venus's atmosphere. By mastering this phase, humanity takes its first step toward exploring and eventually living in the clouds of our celestial neighbor. Airship and drone technologies will be the backbone of mobility and exploration in Venus's atmosphere. These vehicles must be designed to operate in dense, corrosive air while navigating high-speed winds. Airships will serve as the primary mode of transportation within the habitable zone. Their buoyant designs, filled with breathable air or other lifting gases, will allow them to hover and travel with minimal energy expenditure. These airships must be constructed from lightweight, corrosion-resistant materials. Advanced polymers and composites will ensure durability while maintaining flexibility for maneuvering through turbulent conditions. Propulsion systems on airships will need to counteract Venus's strong winds. Electric or hybrid engines powered by solar energy will provide the efficiency and reliability needed for sustained operation. Drones will complement airships by performing tasks that require precision or reach. These smaller, agile vehicles can navigate areas that are too dangerous or inaccessible for larger vessels. Equipped with cameras and sensors, drones will play a vital role in mapping Venus's atmosphere and surface. They can collect data on weather patterns, atmospheric composition, and even the planet's geological features. Autonomous systems will allow drones to adapt to unpredictable conditions. Real-time decision-making will enable them to avoid hazards like turbulence or high-speed wind corridors. Drones can also assist in resource collection. By hovering at specific altitudes, they might extract trace gases or materials from the atmosphere for use in the floating habitats. Both airships and drones will be vital for connecting habitats and supporting a growing infrastructure. They can transport cargo, supplies, and personnel, ensuring a seamless exchange between floating cities. Redundancy will be crucial for both technologies. Backup systems and modular designs will allow for quick repairs or replacements, reducing downtime in such a remote and hostile environment. Energy efficiency will define the success of these vehicles. Lightweight solar panels integrated into airship exteriors or drone surfaces will allow for extended operation without frequent refueling. Together, airships and drones will transform Venus's skies into a navigable and interconnected space. They will bring mobility, exploration, and functionality to an environment that challenges every aspect of human ingenuity. Intercity travel on Venus will rely on a sophisticated network of airships and transport drones. These vehicles will connect floating habitats, enabling the movement of people, goods, and resources across the atmospheric expanse. High-capacity airships will serve as the primary carriers for long-distance travel. Designed for efficiency and safety, these airships will transport passengers and bulk cargo between cities. Smaller, more agile shuttles will complement the larger airships. These vehicles will handle short-distance routes, providing a flexible solution for local and regional travel within the network. Navigation systems will need to account for Venus's dynamic wind patterns. Advanced GPS-style technology, adapted for atmospheric use, will ensure precise routing and collision avoidance. Travel corridors will be established to maintain order in the skies. Designated airways will help manage traffic and prevent interference between vehicles moving at different speeds or altitudes. Energy autonomy will be essential for these transport systems. Airships and drones will rely on solar-powered engines, backed by onboard storage systems, to ensure uninterrupted operation. Maintenance hubs will form an integral part of the infrastructure. These floating service stations will provide refueling, repairs, and inspections to keep the transport network running smoothly. Safety protocols will address the challenges of operating in a corrosive and turbulent environment. Redundant systems and real-time monitoring will minimize the risk of accidents during transit. Communication between cities and vehicles will require robust, high-frequency signal networks. These systems will ensure that airships and drones stay connected even during adverse weather conditions. Cargo logistics will depend on modular containers designed for rapid loading and unloading. These containers will streamline the movement of supplies, reducing turnaround times at each city. Emergency transport systems will also be incorporated. Rapid response airships or drones will provide medical evacuations and urgent deliveries when seconds count. A well-designed intercity travel network will turn Venus's atmosphere into a connected ecosystem. By linking floating cities, this infrastructure will foster collaboration, trade, and the expansion of human presence in the clouds. Resource transport systems on Venus will form the backbone of sustained habitation. Moving essential materials between floating habitats and extraction sites will require efficient and reliable logistics. Airships will be the primary carriers for large-scale resource transport. These vessels, equipped with spacious cargo holds, can move harvested gases, raw materials, and processed goods across long distances. Specialized drones will handle smaller targeted deliveries. These agile vehicles can quickly transport resources to specific locations, especially in areas where larger airships cannot maneuver. Modular cargo pods will streamline loading and unloading operations. These pods can be standardized for various resources, allowing for quick swaps and minimizing delays in the supply chain. To ensure safety, cargo airships will be designed with redundancy and protective features. This is especially critical when transporting volatile materials or delicate equipment. Automated systems will play a key role in managing resource flow. Advanced software will optimize routes, schedule deliveries, and monitor inventory levels to prevent bottlenecks. Energy autonomy will be crucial for these systems. Solar-powered engines paired with robust energy storage will ensure that transport vehicles remain operational regardless of atmospheric conditions. Resource hubs will act as central nodes in the transport network. These floating facilities will store, process, and distribute materials, serving as logistical bases for nearby habitats. Real-time tracking systems will monitor the movement of resources throughout the network. This technology will provide transparency and allow for quick adjustments in case of delays or disruptions. Waste materials and recyclables will also be part of the transport system. Dedicated drones and airships will collect these materials and deliver them to recycling or disposal facilities within the network. Emergency resource transport systems will ensure critical supplies, such as food, oxygen, or medical equipment, reach their destinations quickly. These systems will prioritize urgent needs and maintain readiness for unexpected situations. Efficient resource transport will enable Venus's floating cities to function as a cohesive and sustainable ecosystem. By seamlessly moving materials, this network will support growth, exploration, and long-term survival in the clouds. Navigating Venus's winds presents one of the most complex challenges for aerial mobility. The super-rotating atmosphere, with winds reaching up to 360 kilometers per hour, creates constant motion that must be managed with precision. These winds vary dramatically with altitude, creating layered currents that can shift direction and intensity. Vehicles must be equipped with advanced sensors to detect these changes in real time and adjust their course accordingly. High-speed winds can place immense stress on the structural integrity of airships and drones. Designs will need to incorporate reinforced frameworks and materials capable of withstanding these forces over extended periods. Turbulence is another major concern, especially near the boundaries between different wind layers. Stabilization technologies, such as gyroscopic systems or active thrusters, will help vehicles maintain steady flight. Predicting wind patterns on Venus is far more difficult than on Earth. Rapid shifts in atmospheric conditions mean that navigation systems must rely on real-time data rather than pre-programmed routes. Autonomous control systems will be essential for safe operation. These systems can process environmental data instantly, making adjustments to keep vehicles on course despite unpredictable conditions. Communication delays between Venus and Earth add another layer of complexity. Vehicles will need to function independently, with onboard systems capable of making split-second decisions during emergencies. The corrosive atmosphere compounds these challenges. Wind-blown sulfuric acid particles can erode surfaces and interfere with sensitive instruments, requiring frequent maintenance and protective measures. Energy efficiency becomes a critical factor in combating strong winds. Propulsion systems must generate enough thrust to navigate effectively without exhausting their power reserves. Collaboration between vehicles can help overcome these challenges. Swarms of drones or networks of airships can share data on wind conditions, creating a coordinated response to Venus's turbulent environment. Vehicle positioning systems will need to account for drift caused by the relentless winds. Precise calculations will ensure that floating habitats and transport systems remain aligned with their intended locations. Despite these obstacles, mastering the winds of Venus is achievable. With advanced engineering and adaptive technologies, we can turn these challenges into opportunities for exploration and mobility. Venus's atmosphere and geology hold untapped potential for resources that could sustain human habitation. The dense carbon dioxide layer offers an abundant supply of raw material for various industrial and life support applications. Carbon dioxide can be processed to produce oxygen for breathing and carbon for manufacturing. Advanced chemical reactors would enable this transformation, creating essential resources directly from the atmosphere. Nitrogen, another component of Venus's atmosphere, is vital for agriculture and life support systems. Extracting and isolating nitrogen could support the development of sustainable food production. Sulfur compounds present in the atmosphere offer opportunities for chemical processing. These materials could be converted into sulfuric acid for industrial use or broken down into other valuable elements. Trace amounts of water vapor found in the atmosphere represent a crucial resource. Harvesting and purifying this vapor could provide a renewable source of water for drinking, farming, and other essential needs. The planet's rocky surface may contain valuable minerals, though accessing these resources is a significant challenge. Future exploration could reveal deposits of metals like iron or aluminum beneath the hostile conditions. Geological studies suggest that Venus's crust may hold similarities to Earth's, potentially including rare materials. If extraction technologies advance, these deposits could support construction and technological development. Renewable energy from the sun is another invaluable resource. Venus's proximity to the sun provides an opportunity to harness solar power at scales unparalleled in other parts of the solar system. The thick atmosphere also creates unique opportunities for thermal and kinetic energy harvesting. These renewable energy sources could supplement solar power, ensuring a diversified energy grid. Resource recycling within the floating habitats will maximize efficiency. By reprocessing waste materials and atmospheric gases, habitats can reduce dependence on new resource extraction. Venus's resources offer not only practical benefits, but also scientific value. Studying the atmosphere and surface could unlock insights into planetary formation and the evolution of extreme climates. With innovative technologies, Venus's natural abundance can be transformed into the building blocks of a thriving society. Each resource brings us closer to creating a sustainable future in the clouds. Resource extraction on Venus will rely on innovative techniques designed to overcome its extreme conditions. The dense atmosphere and corrosive clouds require specialized equipment to safely harvest usable materials. Atmospheric skimming will be a primary method for collecting gases like carbon dioxide and nitrogen. Large-scale collectors attached to airships or floating habitats could filter these elements directly from the surrounding air. For water vapor, advanced condensation systems will capture and purify trace amounts found in the atmosphere. These systems must operate efficiently to ensure a steady supply of this essential resource. Electrochemical processes will be key to breaking down atmospheric components. By splitting carbon dioxide, oxygen and carbon can be extracted for life support and industrial uses. Sulfuric acid, abundant in the clouds, can be processed into sulfur or neutralized for use in various chemical applications. Corrosion-resistant equipment will be necessary for handling this material safely. If surface mining becomes feasible in the future, robotic probes will play a critical role. These automated systems would operate remotely, collecting samples and extracting minerals while withstanding Venus's hostile environment. Energy-efficient drilling techniques may allow access to subsurface resources. Advanced insulation and cooling technologies will protect equipment from the intense heat and pressure of the planet's crust. Floating habitats could also deploy tethered extraction systems. These devices would lower into denser atmospheric layers to collect specific materials before returning to safer altitudes. Resource processing will often occur directly within the habitats. Modular refineries and 3D printing systems will convert raw materials into finished goods, reducing the need for complex supply chains. Energy from solar panels or wind systems will power these extraction processes. This renewable energy ensures that resource collection remains sustainable and minimizes environmental impact. Collaborative resource sharing between habitats will optimize efficiency. By pooling collected materials, cities can focus on specialized extraction methods without redundancy. Techniques for resource extraction on Venus are as much about ingenuity as practicality. Each method must adapt to the planet's unique environment while laying the foundation for a self-sufficient society in the skies. The atmospheric gases of Venus present a wealth of opportunities for industrial applications. These abundant resources can be harnessed to sustain life and drive production processes within floating habitats. Carbon dioxide, which dominates the atmosphere, is a versatile raw material. It can be converted into oxygen for breathing or used in carbon-based manufacturing, forming the backbone of a sustainable industrial ecosystem. Carbon extracted from the atmosphere can also be used to produce advanced materials like graphene or carbon composites. These lightweight yet durable substances are ideal for constructing and maintaining floating habitats. Nitrogen, though less abundant, is critical for agriculture and life support systems. Extracted nitrogen can be transformed into ammonia or other compounds essential for fertilizing crops grown in controlled environments. Sulfuric acid, a challenge for habitation, is also an opportunity for industry. Neutralizing and processing it can yield sulfur, a key ingredient in chemical manufacturing and energy storage solutions. The potential for water extraction opens additional industrial pathways. Trace water vapor from the atmosphere can be purified and used in processes like electrolysis, which produces hydrogen fuel. Hydrogen derived from atmospheric processing can be stored and used in fuel cells. These cells provide a clean, efficient energy source, supporting both industrial systems and daily operations within the habitats. Atmospheric gases could also support energy-intensive processes like metal refining. By using carbon and hydrogen as reducing agents, metals extracted from the surface or imported from Earth can be processed efficiently. Ammonia synthesis, a cornerstone of industrial chemistry, could thrive using Venus's atmospheric nitrogen and hydrogen from water vapor. This compound is essential for creating fertilizers, refrigerants, and cleaning agents. Methane, created from atmospheric carbon and hydrogen, could serve as a fuel or chemical feedstock. Its versatility makes it a valuable component of an interconnected industrial network. The unique composition of Venus's atmosphere may also enable entirely new industrial techniques. The dense gases and extreme conditions offer opportunities for experiments that are impossible in Earth's environment. Harnessing atmospheric gases transforms Venus's challenges into advantages. By integrating these resources into industrial systems, floating habitats can achieve both sustainability and self-sufficiency in the clouds. Self-sufficiency on Venus begins with utilizing local materials to minimize dependence on resupply missions from Earth. The abundance of carbon dioxide, nitrogen, and sulfur in the atmosphere provides a foundation for creating essential resources. Carbon extracted from the atmosphere can support the production of building materials like carbon composites and graphene. These lightweight yet strong materials are ideal for expanding and maintaining floating habitats. Oxygen, a byproduct of splitting carbon dioxide, ensures a continuous supply for life support systems. Combined with hydrogen harvested from trace water vapor, it can also produce water for drinking and farming. Nitrogen plays a crucial role in sustaining agriculture. By combining it with hydrogen, ammonia can be synthesized to fertilize crops, enabling food production entirely within the habitats. Sulfur harvested from the atmosphere can be used in a variety of industrial applications. From producing batteries to creating chemicals for water purification, it's a versatile and valuable resource. Hydrogen generated from water vapor opens additional pathways to self-sufficiency. It powers fuel cells, serves as a reducing agent in industrial processes, and supports the synthesis of compounds like methane and ammonia. Renewable energy sources like solar and wind ensure that resource processing and manufacturing remain sustainable. By powering extraction and production systems locally, habitats reduce their environmental impact while enhancing independence. Recycling systems will amplify the efficiency of local material use. By recovering and reprocessing waste, habitats can create a closed-loop system where nearly all materials are reused. 3D printing technologies could transform harvested materials into tools, components, and even structural elements. This flexibility allows habitats to produce what they need on demand, adapting to changing requirements. Advanced chemical reactors will enable continuous conversion of atmospheric gases into usable products. These systems will function as the industrial heart of the habitats, turning raw materials into necessities for life and development. Efforts to integrate local materials into habitat systems will also provide opportunities for research and innovation. Discovering new applications for Venus's resources could lead to technological breakthroughs. Building self-sufficiency through local materials ensures that habitats on Venus are more than sustainable. They become thriving ecosystems capable of growing and evolving without reliance on distant Earth. Ethical considerations in resource use on Venus are as important as the technologies we develop. Extracting materials from the atmosphere or surface must be balanced with preserving the integrity of the planet itself. One key consideration is the potential for unintended environmental consequences. While Venus may seem lifeless, our activities could alter its atmosphere in ways that disrupt future exploration or scientific study. Respect for the unique characteristics of Venus's environment is essential. Even in an uninhabitable world, the preservation of natural conditions ensures that humanity learns from the planet without causing irreversible damage. Resource extraction must prioritize sustainability over exploitation. Creating systems that replenish or recycle materials will prevent overuse and maintain balance within the floating cities. Collaboration between nations and organizations will be crucial to establishing ethical guidelines. By ensuring fair and transparent use of resources, Venus can serve as a model for responsible space exploration. Attention must also be given to the equitable distribution of resources among habitats. Inequities in resource allocation could lead to conflict, undermining the cooperative spirit required to thrive in such a challenging environment. Cultural and scientific values must guide our approach. Venus is a unique frontier, and the way we treat its resources reflects our collective responsibility as stewards of the solar system. The extraction process itself must avoid unnecessary destruction. Technologies should aim for minimal disruption, ensuring that operations do not generate excessive waste or contamination. Future generations will depend on the resources of Venus. Ethical practices today ensure that the planet remains a viable destination for research, habitation, and innovation. Developing and adhering to a shared legal framework will help regulate resource use. International agreements can establish clear boundaries for what is acceptable, protecting Venus from overexploitation. Transparency in decision-making is critical. Open communication about how resources are being used and the impact of those actions will foster trust among all stakeholders involved in Venus's colonization. Ethical resource use on Venus isn't just a choice, it's a necessity. By respecting the planet and its potential, we ensure that humanity's expansion into the solar system is both sustainable and principled. Temperature regulation systems on Venus will be critical for maintaining livable conditions within floating habitats. The extreme heat, even at higher altitudes, requires innovative solutions to keep internal environments stable and safe. Thermal insulation will form the first line of defense. Advanced materials such as aerogels or multi-layer reflective coatings can prevent external heat from penetrating the habitat's structure. Active cooling systems will play a central role in maintaining internal temperatures. Radiative cooling panels can dissipate excess heat into space, ensuring that habitats remain comfortable even in high thermal conditions. Liquid-based cooling loops may also be employed, circulating coolant fluids to absorb and transfer heat away from living and working areas. These systems can operate continuously, powered by solar energy. Energy-efficient climate control systems will balance cooling with minimal power consumption. Smart algorithms will adjust cooling output dynamically, responding to environmental and internal conditions in real time. Ventilation systems will work alongside cooling technologies to regulate airflow. By moving cooled air throughout the habitat, they ensure even temperature distribution and prevent hotspots. Thermal energy storage could enhance efficiency further. Excess heat collected during the day can be stored and released during cooler periods, reducing the strain on active cooling systems. Shielding against solar radiation will be another essential component. Reflective exteriors will minimize heat absorption, while internal systems focus on dissipating any residual energy. Temperature regulation must also consider the effects of human activity. Heat generated by machinery, electronics, and daily life will require continuous management to maintain balance. Redundant systems will ensure reliability. Backup cooling mechanisms and fail-safe protocols will prevent critical failures, even during unexpected surges in temperature. Maintenance and monitoring will be key to long-term functionality. Regular diagnostics and automated repairs will keep temperature regulation systems operating efficiently in Venus's challenging environment. Effective temperature control not only ensures survival, but also supports productivity and well-being. By creating stable, comfortable spaces, these systems enable life to flourish in the clouds of Venus. Oxygen production on Venus will be vital for sustaining life within floating habitats. With the atmosphere nearly devoid of oxygen, systems must create it from local resources, ensuring a continuous and reliable supply. Splitting carbon dioxide from the atmosphere is the most promising method for oxygen production. Electrolysis or photocatalytic processes can break CO2 into breathable oxygen and useful carbon byproducts. Water vapor, though scarce, can also contribute. Electrolysis of water harvested from the atmosphere will yield both oxygen and hydrogen, supporting life support systems and energy production. Storage systems will ensure oxygen availability even during production disruptions. Pressurized tanks or cryogenic storage units will maintain reserves for emergencies or high-demand periods. Air circulation systems will distribute oxygen evenly throughout the habitat. These systems must maintain consistent pressure and prevent localized shortages in enclosed living spaces. Air quality monitoring will be critical to maintaining a safe environment. Sensors will continuously measure oxygen levels, carbon dioxide buildup, and potential contaminants, adjusting ventilation as needed. Carbon dioxide removal systems will prevent dangerous concentrations from accumulating. These systems will scrub excess CO2, recycling it back into oxygen production or storing it for industrial uses. Filtration technologies will protect against atmospheric contaminants. Sulfuric acid droplets or trace gases that infiltrate the habitat must be neutralized to ensure breathable air remains pure. Humans and plants can work symbiotically to regulate air quality. Controlled ecosystems within the habitat will use photosynthesis to naturally recycle carbon dioxide into oxygen while providing food and psychological benefits. Redundancy in oxygen production is non-negotiable. Backup systems will ensure uninterrupted oxygen supply, even during equipment failures or maintenance cycles. Energy-efficient designs will reduce the strain on production systems. By minimizing air loss and recycling resources, habitats can maintain high air quality without excessive energy consumption. Oxygen production and air quality management are about more than survival. They are the foundation for creating a healthy, thriving community in Venus's skies, where every breath supports exploration and life. Water sourcing on Venus will rely on capturing trace amounts of vapor from the atmosphere. Even in small concentrations, advanced condensation systems can extract and purify this essential resource. High-efficiency condensers will collect water directly from the air. These systems will operate continuously, using minimal energy while maximizing recovery rates in the challenging atmospheric conditions. Water recycling will be equally critical, ensuring minimal waste. Closed-loop systems will purify and reuse water from every source, including waste streams, condensation, and agricultural runoff. Filtration systems will remove impurities and contaminants from recycled water. Advanced membranes and chemical treatments will ensure that the water is clean and safe for drinking, cooking, and other uses. Desalination techniques may also play a role. If water vapor is contaminated with atmospheric salts or acids, specialized systems will separate these compounds during the purification process. Energy-efficient recycling methods will reduce the burden on water collection systems. By optimizing the reuse of existing water, habitats can minimize the need for fresh sourcing. Agriculture within the habitats will require careful water management. Drip irrigation and hydroponic systems will use precise amounts of water to grow crops while capturing and reusing any excess. Humidity control will aid in water recovery. Atmospheric moisture from within the habitat can be condensed and reintroduced into the system, reducing overall demand. Storage systems will ensure a steady water supply even during disruptions. Tanks or reservoirs within the habitats will hold reserves for emergencies, ensuring that life support systems remain stable. Monitoring systems will track water use across all activities. These sensors will detect leaks, optimize distribution, and ensure that every drop is accounted for within the closed-loop system. Redundancy in water recycling systems will safeguard against failures. Backup units will take over seamlessly if primary systems require maintenance or repair. Water sourcing and recycling are more than technological challenges. They form the lifeblood of a sustainable habitat, enabling life and industry to flourish in Venus's unforgiving atmosphere. Food production on Venus will depend on innovative agricultural systems that maximize efficiency in limited spaces. Hydroponics and aeroponics will be the primary methods, allowing plants to grow without soil by delivering nutrients directly through water or mist. These systems can be tailored to fit the unique constraints of floating habitats. Vertical farming structures will utilize multiple levels to grow a variety of crops, making the most of the available area. LED lighting will simulate sunlight for crops, enabling growth regardless of the conditions outside. These lights can be fine-tuned to provide optimal wavelengths, increasing productivity and reducing energy consumption. Water used in these systems will be recycled continuously. Advanced filtration and nutrient recovery processes will ensure minimal waste while maintaining a consistent supply of essential elements for plants. Carbon dioxide from the atmosphere will serve as a valuable resource. Plants will convert it into oxygen and biomass through photosynthesis, creating a natural balance within the habitat's ecosystem. Fast-growing and high-yield crops will be prioritized. Plants like leafy greens, herbs, and certain vegetables can provide essential nutrients with shorter growing cycles, ensuring a steady food supply. Edible algae and fungi could complement traditional crops. These organisms thrive in compact, controlled environments and offer high nutritional value, making them ideal for habitat-based farming. Incorporating aquaponics systems would add fish to the equation. Fish farming combined with hydroponic crops creates a symbiotic system where waste from the fish fertilizes plants, and plants clean the water for the fish. Genetic modifications or selective breeding may optimize crops for the unique conditions of Venus. Plants could be engineered to thrive in lower pressures or to require fewer resources, further increasing efficiency. Automated systems will monitor and manage agricultural operations. Sensors and AI-driven tools will adjust water, light, and nutrients in real time, ensuring maximum productivity with minimal human intervention. Community involvement in farming could foster a connection to the food supply. Habitat residents may engage in gardening, providing psychological benefits while contributing to the ecosystem. Food production methods on Venus will do more than sustain life. They will create a closed-loop system that integrates seamlessly with water recycling and oxygen production, supporting a thriving and self-sufficient community. Living in floating habitats on Venus will bring unique psychological challenges. Isolation from Earth and the harsh environment outside will require careful planning to support residents' mental health and well-being. A strong sense of community will be essential. Social spaces and shared activities can foster connections among residents, reducing feelings of loneliness and creating a sense of belonging. Access to natural elements, even within artificial environments, can have significant psychological benefits. Indoor gardens, simulated sunlight, and water features will help create a calming atmosphere. Opportunities for personal growth and self-expression will support mental health. Spaces for art, music, and learning can give residents an outlet for creativity and a sense of purpose. Regular communication with Earth will maintain ties to family and friends. Advanced communication technologies will ensure that residents can stay connected despite the vast distance. Physical fitness will also play a crucial role in mental well-being. Exercise facilities, tailored to the limited space within habitats, will provide both physical and psychological benefits. Privacy will be an important consideration. While community is vital, individuals will also need private areas where they can retreat and recharge in solitude. Routines and structure will help residents adapt to life in the clouds. A balance of work, recreation, and rest will create stability and prevent burnout in the isolated environment. Psychological support systems will include trained counselors and virtual therapy options. These resources will be readily available to address stress, anxiety, or other mental health concerns. A sense of purpose will be central to sustaining morale. Whether through scientific research, habitat maintenance, or community projects, residents will need meaningful roles to contribute to the mission. Preparedness for emergencies will reduce fear and build confidence. Regular drills and clear protocols will ensure that residents feel secure and capable of handling unexpected situations. Psychological considerations go beyond survival. They aim to create a thriving community. By addressing these needs, life on Venus can be as fulfilling as it is innovative. The scientific goals for Venus extend beyond exploration and settlement, aiming to uncover the mysteries of a planet so similar yet so different from Earth. Each discovery could reshape our understanding of planetary systems and habitability. One primary goal is to study Venus's atmosphere, particularly the mechanisms behind its runaway greenhouse effect. Understanding this phenomenon could provide critical insights into climate processes on Earth and other planets. Exploring the planet's geology is another priority. By studying the surface composition and volcanic activity, scientists can learn about Venus's tectonic history and its potential for hidden resources. Venus's unique cloud layers hold the key to many unanswered questions. Research into their composition, dynamics, and role in the planet's energy balance could reveal new atmospheric processes. Astrobiology is also a focus, investigating the possibility of microbial life in the temperate cloud layers will test the limits of habitability in extreme environments and expand the search for life beyond Earth. Unraveling Venus's magnetic field, or lack thereof, could shed light on why its atmosphere remains so dense despite the solar wind. These findings might explain why Venus and Earth evolved so differently. Studying Venus's winds and weather patterns will contribute to the broader understanding of planetary climates. Insights from these studies could improve weather modeling on Earth and for future interplanetary missions. Venus offers a natural laboratory for extreme chemistry. Research into the reactions occurring in its dense atmosphere could lead to breakthroughs in materials science and industrial processes. Mapping the planet's surface with high-resolution imaging will uncover hidden geological features. These maps will guide exploration efforts and reveal the history of Venus's impact craters and volcanic plains. Long-term observation of solar interactions with Venus's atmosphere will enhance our understanding of planetary atmospheres across the solar system. These studies could inform the design of more effective space missions. The potential for comparative planetology is immense. By studying Venus alongside Earth and Mars, scientists can piece together the story of how rocky planets evolve under different conditions. Every scientific goal for Venus contributes to a larger purpose. Through exploration and discovery, Venus becomes not just a destination, but a stepping stone in humanity's quest to understand the universe. Researching Venus's atmospheric dynamics is critical to understanding its extreme environment. The atmosphere's unique behavior, including super-rotating winds, holds valuable clues about planetary weather systems. The phenomenon of superrotation, where winds travel faster than the planet rotates, is a major focus. Studying this effect could reveal the mechanisms driving such rapid atmospheric motion and how it influences global climate. Vertical wind layers in Venus's atmosphere vary significantly in speed and direction. Understanding how these layers interact will help map the planet's complex weather patterns and turbulence. Venus's clouds are another key area of study. These dense layers, composed largely of sulfuric acid, play a significant role in reflecting sunlight and trapping heat, creating a dynamic and challenging environment. Temperature gradients across the atmosphere will provide insight into energy transfer processes. Research in this area could improve models of atmospheric heating and cooling on other planets. Tracking weather systems on Venus, such as wave-like formations or storm patterns, will enhance understanding of atmospheric stability. These studies could reveal similarities and differences with Earth's weather. The interaction between Venus's surface and its lower atmosphere is particularly intriguing. Investigating how heat and gases move between these regions will offer clues about the planet's volcanic activity and tectonics. Chemical processes in the atmosphere are crucial for understanding its evolution. Researchers will examine how elements like carbon, sulfur, and nitrogen cycle through the dense air. Venus's lack of a magnetic field means its upper atmosphere interacts directly with the solar wind. This interaction is key to studying how planetary atmospheres erode over time in harsh solar conditions. Venus's atmospheric pressure is among the highest of any terrestrial planet. Understanding how gases behave under such extreme conditions can lead to advancements in materials science and engineering. Data from Venus could also refine predictive models for Earth's climate. By comparing atmospheric dynamics, scientists can better anticipate how changes in greenhouse gas concentrations affect global temperatures. Researching atmospheric dynamics on Venus goes beyond planetary science. It has the potential to advance our understanding of universal weather systems, offering lessons that apply to other worlds and even our own. Geological studies of Venus's surface offer a window into its violent and dynamic past. Despite the challenges of direct exploration, remote sensing and radar mapping provide valuable insights. Venus's surface is dominated by vast volcanic plains. Research into their formation can reveal the scale and frequency of volcanic activity, offering clues about the planet's internal heat and mantle dynamics. Large shield volcanoes, some towering higher than any on Earth, suggest a history of intense and prolonged eruptions. Studying these features could help understand how Venus lost its water and developed its current atmosphere. Impact craters scattered across the surface provide a record of celestial collisions. Their relatively uniform distribution hints at a planetary resurfacing event that erased earlier geological features. Tesserae, Venus's oldest and most complex surface formations, are a key focus of study. These regions may hold evidence of ancient tectonic activity, offering a glimpse into a time when the planet's crust was more dynamic. The planet's lack of plate tectonics presents a stark contrast to Earth. Researching why Venus's crust evolved differently can deepen our understanding of tectonic processes on rocky planets. Rift valleys and mountain ranges indicate localized crustal movement. These features suggest that Venus's surface experiences periodic deformation, which could be tied to internal pressures or heat flow. The possibility of active volcanism on Venus remains an exciting prospect. Detecting thermal anomalies or sulfur gas emissions would confirm that the planet is still geologically alive. Exploring Venus's crustal composition is crucial for understanding its geological history. Analyzing the mineral content and rock formations can reveal details about the planet's early environment and evolution. Lava flows visible in radar images provide a timeline for recent geological activity. Their distribution and layering patterns can help determine when and how Venus's surface was last reshaped. Studying the surface also holds implications for future exploration. Understanding its rugged terrain and the composition of the ground will guide the design of landers and surface probes. Geological studies of Venus not only uncover the planet's past, but also offer comparisons to Earth's development. By piecing together its story, we gain a broader perspective on the forces that shape terrestrial worlds. The potential for discovering life on Venus lies in its mysterious atmosphere. While the surface is inhospitable, the cloud layers present a more temperate environment where life might exist. In the upper atmosphere, temperatures and pressures are similar to those on Earth. This region, high above the scorching surface, has become the focus of astrobiological interest. Recent studies have detected traces of phosphine gas in the Venusian atmosphere. On Earth, this compound is often associated with biological processes, raising questions about its origin on Venus. Microbial life, if it exists, could survive within the cloud layers. These microorganisms would need to adapt to acidic conditions and derive energy from chemical reactions in the atmosphere. The presence of water vapor, though minimal, is another intriguing factor. Even small amounts of water could support microbial ecosystems in isolated pockets of the clouds. The dense atmosphere might also provide a stable environment for certain extremophiles. These life forms, similar to those on Earth, could thrive under extreme conditions of acidity and limited nutrients. Organic molecules, the building blocks of life, might form naturally in the Venusian atmosphere. Their presence could suggest prebiotic processes or even active biological activity. Studying the atmospheric chemistry will help rule out non-biological explanations for potential biosignatures. This research is essential to understanding whether life has adapted to such an extreme world. Advanced missions equipped with sampling technologies could collect and analyze atmospheric particles. These missions would aim to detect microbial life directly or identify clear indicators of biological processes. Venus also provides an opportunity to study life's potential beyond its traditional boundaries. Discovering life here would redefine our understanding of habitability and expand the search for life in the universe. Exploring Venus's potential for life is not just about finding living organisms. It's about understanding how life might arise and adapt under conditions vastly different from those on Earth. The search for life on Venus holds profound implications for science and humanity. It challenges our assumptions, inspires exploration, and brings us closer to answering one of the universe's greatest mysteries. Science will be the driving force behind the colonization of Venus. Every aspect of living and thriving in its atmosphere will rely on breakthroughs in research and innovation. Understanding Venus's unique environment is the first step. Scientific exploration of its atmosphere, surface, and weather systems will provide the data needed to design sustainable habitats. Advanced material science will be critical. Developing corrosion-resistant and lightweight materials ensures structures can withstand Venus's harsh atmospheric conditions while remaining efficient and durable. Life support systems will depend on biology and chemistry research. Processes to recycle air, water, and nutrients must be optimized for closed-loop ecosystems, reducing reliance on Earth-based supplies. Energy generation and storage solutions will require cutting-edge engineering. Solar, wind, and alternative energy systems must be adapted to the planet's unique conditions for reliable power supply. Atmospheric studies will inform resource extraction techniques. Understanding the composition and dynamics of Venus's air will allow scientists to harvest gases and convert them into usable materials. Geological research will shape future exploration of the surface. Studying Venus's crust will guide plans for potential mining operations or the deployment of surface probes. Science will also drive the search for life. Investigating Venus's potential for biology deepens our understanding of habitability and expands the scope of astrobiology. Robotics and automation will play a key role. Machines capable of operating in Venus's extreme environment will handle tasks too dangerous or complex for humans. Scientific collaboration will be essential. By pooling knowledge and resources, international teams can tackle the challenges of Venusian colonization more effectively than working alone. Data gathered from Venus will have applications beyond the planet itself. Lessons learned could inform the colonization of other worlds, improving humanity's capacity to live in extreme environments. Science transforms the dream of Venus colonization into reality. Through discovery and innovation, it provides the tools and knowledge needed to build a future in the clouds. Partnerships between nations and agencies will be essential for the successful colonization of Venus. No single entity has the resources or expertise to tackle the challenges of such a complex mission alone. International collaboration can pool knowledge and technology. By combining efforts, scientists and engineers from around the world can develop more advanced systems and share the costs of exploration. Space agencies like NASA, ESA, and Roscosmos can bring decades of experience to the table. Each organization has unique strengths that can contribute to different aspects of Venus colonization. Private companies will also play a critical role. Their innovation and efficiency in developing space technologies can complement the expertise of government agencies. Academic institutions can provide research support, offering insights into everything from atmospheric chemistry to robotics. These collaborations ensure that the latest scientific advancements are integrated into the mission. Partnerships foster shared ownership of the endeavor. By involving multiple nations, the benefits and responsibilities of Venus colonization are distributed, reducing the risk of conflict over resources or territory. Clear frameworks for collaboration will be necessary. Agreements on funding, technology sharing, and resource allocation will create a foundation for effective partnerships. International regulatory bodies may oversee key aspects of the mission. These organizations can ensure that operations on Venus adhere to ethical and sustainable practices. Cultural exchange between participating nations can enhance collaboration. Sharing perspectives and approaches to problem-solving can lead to more creative and comprehensive solutions. Public engagement is another benefit of partnerships. Global cooperation can inspire support and enthusiasm for the mission, uniting humanity around a shared goal. Partnerships also create redundancy and resilience. With multiple contributors, the mission becomes less vulnerable to setbacks from any single nation or organization. The challenges of Venus demand a collective effort. Through partnerships, humanity can combine its knowledge, resources, and determination to reach new heights in exploration and discovery. Private sector involvement will be a driving force in the colonization of Venus. Companies bring innovation, efficiency, and a willingness to take calculated risks that accelerate progress. Space companies like SpaceX and Blue Origin have already demonstrated their ability to revolutionize launch systems. Their expertise can reduce the cost of sending equipment and materials to Venus. Private firms can also focus on specialized technologies. From habitat construction to resource extraction, companies can innovate in areas that complement government-led initiatives. The private sector's investment in renewable energy systems will be vital. Companies developing solar panels, energy storage, and wind systems can adapt these technologies for Venus's unique environment. Mining and resource processing firms may contribute expertise in extracting and refining materials. Their experience with extreme Earth environments can inform approaches to harvesting Venus's resources. Commercial innovation extends to life support and food systems. Companies working on sustainable agriculture and recycling technologies can tailor their solutions to the constraints of Venusian habitats. Tourism and commercial interests could provide additional funding streams. The prospect of visiting or even living in Venus's floating cities may attract private investment in infrastructure and transportation. Private sector involvement fosters competition, which drives efficiency and reduces costs. Multiple companies vying to provide solutions lead to faster advancements and better outcomes. Collaboration between private companies and government agencies creates synergy. Public funding supports research, while private firms focus on scalable and cost-effective implementation. Ethical frameworks will guide private sector activities on Venus. Agreements will ensure that companies operate responsibly, balancing profit motives with sustainability and shared goals. The entrepreneurial spirit of the private sector brings a dynamic energy to the mission. Their flexibility and innovation make them an essential partner in tackling the challenges of Venus. Through partnerships and innovation, private companies will transform Venus from a distant vision into a tangible reality. Their contributions will help build the systems needed for humanity's next frontier. The history of space exploration offers invaluable lessons for the colonization of Venus. Decades of missions to the Moon, Mars, and beyond have taught us the importance of preparation, innovation, and international collaboration. The Apollo program demonstrated that ambitious goals can be achieved through focused effort. Its success highlights the need for clear objectives and unified direction in tackling monumental challenges. Mars rovers like Curiosity and Perseverance have shown the value of robotic exploration. Their ability to gather data remotely emphasizes the importance of understanding Venus's environment before sending humans. The International Space Station is a testament to the power of cooperation. Built and maintained by multiple nations, it serves as a model for how shared resources and expertise can enable long-term habitation. Failures, such as the loss of Mars' climate orbiter, underscore the need for meticulous planning. Even small miscalculations can have significant consequences, emphasizing the importance of precision and redundancy. The longevity of Voyager and other deep space probes teaches us the value of durable and adaptable technology. Systems designed for Venus must withstand its extremes while maintaining functionality over time. The Hubble Space Telescope has shown the importance of maintenance and upgrades. Ensuring that systems on Venus are accessible for repair will be crucial for sustaining long-term operations. Apollo 13 reminds us that contingency planning is essential. Preparedness for unexpected challenges can mean the difference between mission success and failure in Venus's unforgiving environment. The Mars InSight lander highlights the importance of studying planetary interiors. Similar investigations on Venus could unlock secrets about its geological history and tectonic activity. SpaceX's reusable rockets demonstrate the need for cost-effective systems. Reducing expenses will make colonization sustainable and ensure ongoing support for Venusian settlements. The search for water on the Moon and Mars has reinforced the importance of in-situ resource utilization. Extracting local materials will reduce dependency on Earth and enable greater self-sufficiency on Venus. Every lesson from past missions contributes to the knowledge needed for Venus. By building on these successes and learning from failures, humanity can take its next great step with confidence. Establishing legal and ethical frameworks for Venus colonization is essential to ensure that exploration and habitation are carried out responsibly. These guidelines will define how resources are used and how conflicts are resolved. International agreements like the Outer Space Treaty provide a foundation. They emphasize that space is the province of all humanity, prohibiting claims of sovereignty and prioritizing peaceful exploration. A key legal challenge will be defining property rights. While no nation can claim Venus, clear rules are needed to regulate the use of resources and prevent disputes between stakeholders. Ethical considerations must prioritize sustainability. Resource extraction and habitat expansion should balance human needs with preserving Venus's environment for future research and exploration. Transparent governance structures will ensure accountability. An international body could oversee activities on Venus, ensuring that all actions align with agreed-upon principles and objectives. Human rights protections will be critical in these frameworks. The well-being, safety, and autonomy of habitat residents must be safeguarded as part of the legal system. Fair access to resources will prevent inequality. Guidelines will ensure that no single nation, corporation, or entity monopolizes Venus's materials or opportunities. Cultural heritage must be respected. As humanity extends its reach to Venus, efforts should be made to honor diverse perspectives and include voices from around the world in decision-making. Ethical research practices will guide scientific studies. Experiments on Venus must adhere to principles of integrity, ensuring that data collection and analysis are conducted responsibly. Safety standards will be central to any legal framework. Strict protocols will minimize risks to both humans and the environment, promoting a culture of caution and preparedness. Legal frameworks will also address emergencies. Clear protocols for evacuation, disaster response and support will be critical for managing crises on such a distant frontier. Ethics and law are not barriers to exploration. They are tools for ensuring it is done equitably and sustainably. By establishing robust frameworks, humanity can approach Venus with integrity and foresight. Sharing the benefits of Venus colonization ensures that the advancements made in this ambitious endeavor uplift all of humanity. The knowledge, technologies, and resources gained must be accessible to a global audience. Scientific discoveries on Venus can enhance our understanding of planetary systems. Sharing these insights could inform climate studies on Earth and inspire new approaches to preserving our own environment. Technological innovations developed for Venus will have wide-ranging applications. Breakthroughs in energy, materials, and life support systems can be adapted to improve living conditions and sustainability on Earth. Venus colonization offers an opportunity to foster international collaboration. Sharing the successes and challenges of this mission can strengthen partnerships and build trust between nations. Economic benefits can also be distributed equitably. Industries supporting Venus exploration, from aerospace to renewable energy, can create jobs and spur growth in countries around the world. Educational outreach will inspire the next generation. Sharing the story of Venus colonization can ignite curiosity and encourage young minds to pursue careers in science, technology, and exploration. Cultural representation is key to sharing the benefits. Including diverse voices and perspectives in the mission ensures that the achievements resonate with people from all backgrounds. The resources extracted from Venus must be shared responsibly. Whether through agreements or oversight, the wealth generated should contribute to addressing global challenges like poverty and resource scarcity. Venus colonization will also advance humanity's collective knowledge. Open access to data and research findings will ensure that the entire scientific community benefits from this groundbreaking effort. The mission's success can serve as a unifying symbol. Achieving such a monumental goal together demonstrates what humanity is capable of when working toward a common purpose. Lessons learned from Venus will inform future exploration. Sharing these experiences will guide other nations and organizations as they pursue their own space endeavors. By sharing the benefits, Venus colonization becomes more than a scientific achievement. It becomes a shared legacy, advancing progress and opportunity for all of humanity. Funding initial missions to Venus will require a combination of public, private, and international investments. Such an ambitious project demands a robust financial foundation to cover research, development, and deployment costs. Government funding will play a pivotal role in launching the first missions. National space agencies can allocate resources through budgets dedicated to exploration and scientific discovery. International partnerships can distribute costs among participating nations. By sharing financial responsibilities, the burden on any single country is reduced, making the mission more feasible. Private sector investment can bring additional resources to the table. Companies with interests in space exploration, renewable energy, or advanced technologies may see Venus missions as an opportunity for growth. Public-private partnerships could amplify funding. Collaborative efforts allow governments to leverage private sector innovation while providing financial support to kickstart critical projects. Crowdfunding and public engagement could offer supplementary funding. People inspired by the mission's vision might contribute, fostering a sense of shared ownership and enthusiasm. Philanthropic organizations and foundations may also fund specific aspects of the mission. Their contributions can support research, education, or humanitarian goals linked to Venus exploration. Revenue-generating activities could offset costs. Licensing technologies developed for Venus, or creating commercial opportunities in related industries, provides an additional funding stream. Grants and research incentives can encourage academic institutions to participate. Funding for universities and researchers ensures that cutting-edge science supports mission objectives. Incremental budgeting may ease the financial strain. Spreading costs over multiple years allows governments and organizations to allocate funds gradually while maintaining steady progress. Strategic resource allocation will maximize efficiency. Prioritizing high-impact projects and eliminating waste ensures that every dollar invested moves the mission closer to its goals. Transparency in funding and spending will build trust among stakeholders. Open communication about costs and outcomes ensures continued support from governments, investors, and the public. By pooling resources and leveraging creativity, humanity can finance the journey to Venus. The collaboration required to fund these missions mirrors the cooperative spirit essential for their success. Developing a Venusian economy will be a gradual process, starting with resource utilization and evolving into a complex system of trade and innovation. Economic sustainability will be key to supporting long-term habitation and exploration. The initial foundation will be built on resource extraction. Harvesting atmospheric gases like carbon dioxide, nitrogen, and sulfur can provide essential materials for industrial processes and trade. Local manufacturing will create added value. Using advanced technologies like 3D printing, habitats can convert raw materials into tools, components, and infrastructure, reducing dependence on imports from Earth. Energy production will become a central industry. Solar and wind systems can generate surplus power, which might be stored, used for resource processing, or even exported in some form. Agriculture within habitats will provide not only food, but also economic stability. Surplus crops or bio-based materials could be traded between floating cities or back to Earth. Scientific research will drive early economic activity. Data collected on Venus can be monetized through partnerships with universities, corporations, and governments eager to apply these insights. Tourism may eventually play a role in the Venusian economy. The allure of visiting floating cities in the clouds could attract high-paying visitors, generating revenue for further development. Intercity trade will encourage specialization. Each floating habitat could focus on specific industries or services, creating an interconnected economic network within Venus's atmosphere. Technological innovation developed on Venus will have applications on Earth. Licensing these technologies or exporting intellectual property can create financial returns to support further colonization. A Venusian currency or barter system may emerge to facilitate trade. This economic framework would adapt to the unique needs and limitations of living in the clouds. Sustainability will guide the Venusian economy. Practices that prioritize recycling and renewable resources will ensure that industries thrive without depleting the planet's atmospheric wealth. Economic independence from Earth will be the ultimate goal. By creating self-sustaining industries, Venusian colonies can support themselves and become a vital part of humanity's interplanetary future. The Venusian economy will grow alongside its population, evolving from survival-driven activities into a thriving system of innovation, trade, and collaboration. Each step brings humanity closer to a permanent presence in the clouds. Trade and commerce on Venus will initially revolve around the exchange of essential resources and innovations. The unique conditions of the planet provide opportunities to develop specialized industries that support both local needs and broader markets. The export of advanced technologies developed for Venus could become a cornerstone of its economy. Innovations in energy systems, materials science, and life support technologies will have applications across Earth and other space ventures. Resource trade between floating habitats will encourage interdependence. Each city can focus on specific industries or resource extraction, creating a network of specialized economies within the Venusian atmosphere. Atmospheric harvesting will produce valuable gases like carbon dioxide, nitrogen, and sulfur, which can be processed into industrial chemicals or sold to Earth for research and manufacturing. Renewable energy products might also be exported. Venus's abundant solar power could be used to generate fuels like hydrogen or ammonia, which could then be transported back to Earth or other colonies. Knowledge and data will be key commodities. Insights gained from studying Venus's climate, atmosphere, and geology could be licensed to Earth-based institutions, driving advancements in science and technology. Agricultural products grown in floating habitats may form another trade sector. High-yield crops and bio-based materials could become valuable exports, especially if optimized for long-term storage and transport. Tourism offers a potential high-revenue industry. Venus's floating cities could attract adventurous visitors, creating demand for transportation, accommodations, and unique experiences. Cultural exports may also emerge as a facet of Venusian commerce. Art, music and literature inspired by life in the clouds could gain global appeal, fostering cultural exchange between Venus and Earth. Trade routes will expand as more habitats are established. A thriving system of aerial transport between cities will form the backbone of Venusian commerce, enabling the efficient exchange of goods and resources. Barter systems or local currencies could facilitate trade in the early stages. As the economy matures, a formalized system of credits or digital currency may be introduced to streamline transactions. Venus's trade and commerce potential extends beyond survival. By leveraging its unique environment and innovations, the planet can integrate into humanity's broader economic network, driving progress on multiple fronts. Private investment in Venus colonization will require clear and compelling incentives. By aligning business opportunities with the mission's goals, companies can see long-term value in contributing to this groundbreaking effort. The potential for technological breakthroughs is a major draw. Companies investing in habitat construction, renewable energy, and life support systems could develop innovations with global and interplanetary applications. Access to Venus's unique resources offers another incentive. Harvesting atmospheric gases or exploring mineral deposits could open new markets for raw materials and processed goods. Participation in a high-profile mission enhances brand visibility. Being part of humanity's push to colonize Venus can position companies as leaders in innovation and sustainability. Private firms will benefit from partnerships with government agencies. Shared research and funding reduce financial risk, while collaboration accelerates the development of advanced technologies. Revenue from intellectual property is another motivation. Companies contributing to Venus-specific solutions could patent their technologies, creating long-term income streams through licensing and sales. Tourism presents a lucrative opportunity. Firms investing early in infrastructure for transportation and hospitality could capture the first wave of adventurous travelers to Venus's floating cities. Exclusive contracts for providing essential goods and services offer stability. Companies supplying habitats with tools, food, or energy will secure reliable revenue streams over time. Tax incentives from participating nations can further encourage investment. Governments may offer benefits to companies that support Venusian projects, offsetting the high costs of entry. Collaborative ventures with other private firms create synergies. Shared expertise and resources between companies can reduce costs and increase the profitability of joint projects. Investors are also drawn to the prestige of advancing human frontiers. Contributing to Venus colonization aligns companies with a mission that inspires global attention and support. Long-term profitability ensures private involvement remains sustainable. By tying investment opportunities to future economic systems on Venus, companies gain incentives to stay engaged as the colony grows. Private investment transforms Venus colonization into a shared enterprise. By offering opportunities for innovation, revenue, and global impact, the mission becomes a partnership between public ambition and private vision. Long-term financial sustainability on Venus will depend on creating a self-sufficient economy. By establishing industries that leverage local resources and generate value, the colony can reduce its reliance on Earth. Resource utilization will form the foundation of economic stability. Extracting gases, minerals, and other materials from Venus's atmosphere and surface provides raw materials for trade and local production. Manufacturing industries will add value to extracted resources. Turning raw materials into finished goods, such as construction components or energy systems, creates opportunities for commerce and growth. Energy production offers another avenue for sustainability. Excess power from solar or wind systems could be stored and exported, turning Venus into a hub for renewable energy innovation. Tourism will contribute to financial independence. The unique appeal of Venus's floating cities can attract visitors willing to pay for the experience, generating revenue to reinvest in infrastructure and research. Agriculture within habitats can support both local needs and trade. Surplus food production or bio-based materials could become viable commodities in interplanetary markets. Exporting intellectual property developed on Venus will ensure steady income. Technologies perfected in the harsh Venusian environment can be licensed or sold for use on Earth and beyond. Trade between floating cities will encourage economic specialization. Each city focusing on specific industries fosters interdependence, strengthening the overall economy. Financial systems tailored to Venus will provide stability. A digital currency or credit system can simplify trade and reduce transaction costs, enabling seamless economic activity across habitats. International partnerships will play a role in maintaining sustainability. Continued collaboration with Earth-based organizations ensures access to new markets, funding, and technological support. Education and skill development within the colony will sustain innovation. A skilled workforce ensures that industries continue to grow and adapt to changing needs over time. A focus on recycling and efficiency will reduce costs and waste. Closed-loop systems for air, water, and materials minimize the need for constant resource extraction, enhancing economic resilience. By integrating diverse industries and fostering innovation, the Venusian economy can achieve financial sustainability. This ensures that the colony not only survives but thrives, supporting future generations of exploration and development. Managing extreme conditions on Venus will be one of the greatest challenges for colonization. Every system must be designed to endure the planet's intense heat, crushing pressure, and corrosive atmosphere. Advanced materials will form the foundation of survival. Structures and equipment must resist sulfuric acid corrosion while withstanding the stress of high-speed winds and atmospheric density. Temperature regulation is essential. Cooling systems will maintain habitable conditions within floating cities, using reflective exteriors and radiative panels to dissipate excess heat. Pressure management will protect critical systems. Floating habitats will operate at Earth-like pressures, requiring robust seals and redundancies to prevent atmospheric leaks. Navigation systems must handle turbulent winds. Aircraft and drones navigating Venus's atmosphere will rely on adaptive stabilization technologies to ensure safe and precise movement. Equipment exposed to the environment must have protective coatings. These coatings will shield against sulfuric acid droplets, extending the lifespan of critical systems. Energy systems will need to function in unpredictable conditions. Solar panels and wind turbines must be reinforced to maintain efficiency in Venus's harsh environment. Resource extraction technologies must adapt to high pressures and temperatures. Systems for harvesting gases or minerals will require advanced engineering to operate reliably. Communication systems will overcome atmospheric interference. High-frequency networks and adaptive signal processing will ensure seamless contact between habitats and with Earth. Robotic systems will handle dangerous tasks. Automated probes and machines will perform maintenance or exploration in environments too hazardous for human presence. Regular maintenance will be critical for long-term survival. Automated diagnostics and repair technologies will minimize downtime and keep systems functional in the extreme conditions. Managing these challenges requires constant innovation. By adapting technologies and strategies to Venus's extremes, the colony can establish a secure and thriving presence in the clouds. Isolation on Venus presents significant psychological challenges for its residents. The vast distance from Earth and the confined environment of floating habitats require proactive mental health strategies. Community building will be essential to combat loneliness. Shared spaces and group activities can foster connections, creating a sense of belonging among residents. Access to mental health support must be readily available. Counselors and therapists, both on-site and through virtual sessions, can help individuals manage stress and emotional challenges. Daily routines will provide structure and stability. Clear schedules for work, recreation, and rest help residents maintain a sense of normalcy in an otherwise extraordinary setting. Privacy will balance the communal living environment. Personal quarters designed for comfort and solitude will allow individuals to recharge away from shared spaces. Opportunities for creativity and self-expression will enhance well-being. Spaces for art, music, or personal projects can offer an outlet for stress and a way to build meaningful experiences. Regular communication with loved ones on Earth will maintain emotional connections. Technologies that enable real-time video calls or messages will keep residents linked to their support networks. Access to nature, even simulated, can reduce stress. Indoor gardens, artificial sunlight, and soundscapes mimicking natural environments can improve mood and mental health. Physical fitness will support mental well-being. Exercise facilities tailored to the unique conditions of floating habitats will help residents manage stress and stay active. Recreation and entertainment will play a vital role in maintaining morale. Movies, games, and cultural events can offer relief from the monotony of daily life. Psychological preparedness training will help residents adapt to isolation. These programs will equip individuals with strategies to manage their emotions and build resilience. A strong sense of purpose will anchor mental health. Contributing to the mission's success through meaningful work ensures that residents feel valued and connected to a larger goal. Proactively addressing isolation and mental health ensures that life on Venus is not just survivable, but fulfilling. Supporting emotional well-being allows residents to thrive in this extraordinary environment. Technological failures on Venus present significant risks, demanding robust planning and redundancy. The extreme environment amplifies the consequences of even minor system malfunctions. A critical failure in life support systems could jeopardize breathable air, water, or temperature regulation. Redundant systems and real-time monitoring will be essential to prevent catastrophic outcomes. Power outages could halt vital systems, from oxygen production to communication networks. Backup energy solutions, such as battery reserves or alternative generators, must be ready to activate immediately. Structural breaches caused by material fatigue or environmental damage could expose habitats to the corrosive atmosphere. Rapid repair mechanisms and automated sealing systems will mitigate these risks. Communication failures could isolate habitats, cutting off essential contact with Earth or neighboring cities. Developing resilient networks with multiple pathways ensures uninterrupted connectivity. Propulsion or navigation system failures in transport vehicles could leave them adrift in turbulent winds. Automated stabilization and retrieval systems will reduce the likelihood of loss or collision. Equipment exposed to the environment is especially vulnerable to corrosion or mechanical stress. Regular maintenance and durable materials are critical to preventing sudden malfunctions. Resource extraction systems could fail under extreme pressure or temperature conditions. Designing these systems with adaptable components will allow operations to continue even during partial failures. Fire or chemical leaks within the habitat pose serious safety threats. Advanced detection and suppression systems will contain such incidents before they escalate. Data system failures could disrupt operations or lead to incorrect decisions. Cybersecurity and fail-safe data recovery measures will ensure the reliability of critical information. Robotic systems used for exploration or maintenance may malfunction or become immobilized. Remote override capabilities and redundancy in automation will provide alternative solutions. Emergency response plans will address any scenario, from small system disruptions to large-scale crises. Drills and training will prepare residents to act swiftly and effectively. Anticipating technological failures on Venus is as important as preventing them. By integrating fail-safes and redundancies, habitats can remain resilient in the face of unexpected challenges. Environmental impact on Venus must be carefully managed to preserve the integrity of its unique atmosphere and surface. Even in an uninhabitable world, our activities could alter its delicate balance in unforeseen ways. Resource extraction, if not controlled, could disrupt atmospheric chemistry. Harvesting gases or minerals in excess might lead to changes that impact future exploration or scientific research. Waste generated by habitats must be handled responsibly. Without proper disposal or recycling systems, waste materials could pollute Venus's environment, complicating ongoing operations. Energy production systems, particularly large-scale solar or wind installations, could alter localized atmospheric conditions. Studying their long-term effects will help mitigate unintended consequences. Introducing Earth-based microorganisms through accidents or negligence poses risks to Venus's atmosphere. Strict biosecurity measures will prevent contamination and protect the scientific integrity of the planet. Exploration equipment such as probes or landers must be designed to minimize surface disruption. Preserving Venus's geological features ensures that future studies remain undisturbed. Chemical byproducts from industrial activities must be carefully managed. Venting gases or releasing compounds into the atmosphere could lead to unexpected interactions within Venus's dense air. Expansion of floating habitats may create a cumulative impact. Monitoring their effects on wind patterns and solar reflection will help maintain atmospheric stability. Long-term human presence raises questions about sustainability. Ensuring that habitats operate within a closed-loop system minimizes their environmental footprint on Venus. Transport systems could contribute to atmospheric disturbance. Balancing mobility needs with minimal disruption ensures that operations remain efficient and environmentally conscious. Mining efforts on the surface, if pursued, require strict oversight. The use of automated systems designed for minimal contact will reduce environmental degradation. Preservation of Venus's natural state aligns with ethical exploration practices. By prioritizing minimal impact, humanity can study and utilize the planet without irreparably altering its environment. Understanding and mitigating our environmental impact on Venus ensures that exploration remains sustainable. Every effort to protect its atmosphere and surface safeguards the mission's future and scientific potential. Contingency planning and safety protocols are critical for ensuring the survival and well-being of residents on Venus. Preparedness for emergencies will allow habitats to respond effectively to unforeseen challenges. Redundant systems will form the backbone of safety measures. Backups for life support, energy and communication systems will ensure that essential functions continue during disruptions. Detailed emergency response plans will address a wide range of scenarios. From structural breaches to power failures, clear protocols will guide residents through immediate actions. Regular drills and training sessions will prepare residents for emergencies. Practicing these procedures ensures quick and coordinated responses when real incidents occur. Rapid sealing systems will address atmospheric breaches. Automated barriers and repair mechanisms will prevent corrosive air from entering habitats during structural failures. Fire suppression systems will protect against internal hazards. Advanced detection and containment technologies will quickly neutralize fires or chemical leaks before they escalate. Escape routes and evacuation pods will provide safety during catastrophic events. These systems must be easily accessible and capable of operating independently in Venus's harsh environment. Medical facilities within habitats will handle injuries and emergencies. Stockpiles of supplies and access to telemedicine support from Earth will enhance the capability to address health crises. Communication redundancies will maintain contact during disruptions. Multiple pathways for data and voice communication will ensure that habitats remain connected to each other and to Earth. Monitoring systems will provide real-time alerts for environmental or mechanical issues. Sensors and diagnostic tools will detect problems early, allowing for preventive action. Resource stockpiles will support survival during extended crises. Food, water, and energy reserves must be sufficient to sustain residents while repairs are made. A culture of safety and readiness will empower residents. By fostering awareness and encouraging proactive measures, contingency planning becomes an integral part of daily life. Contingency plans are not just about responding to emergencies. They represent a commitment to resilience, ensuring that life on Venus can endure and adapt to any challenge. Establishing a timeline for Venus colonization requires breaking the mission into achievable milestones. Each step builds the foundation for the next, ensuring steady progress toward long-term habitation. The first phase involves robotic exploration. Over the next decade, advanced probes and drones will map Venus's atmosphere and surface, gathering critical data for future missions. Simultaneously, technology development will accelerate. By the mid-2030s, key systems like atmospheric harvesting units, advanced materials, and autonomous navigation technologies will be ready for deployment. By the late 2030s, test platforms will begin operating in Venus's upper atmosphere. These small, unmanned prototypes will validate designs for floating habitats and resource extraction systems. In the 2040s, the first human-operated missions will commence. Crews will live aboard specialized research stations, conducting experiments and refining life support systems for extended stays. The mid-2040s will see the construction of permanent floating habitats. These cities in the sky will use locally harvested resources, transitioning from reliance on Earth to self-sustainability. By the 2050s, intercity networks will begin forming. Trade, transport, and communication systems will link multiple habitats, creating a cohesive Venusian infrastructure. Scientific research will expand throughout the process. By the 2060s, Studies of Venus's geology, climate, and potential biosignatures will provide a deeper understanding of the planet. Tourism and commercial ventures could emerge as early as the late 2060s. These industries will generate revenue and inspire global interest, supporting the economic stability of the Venusian colony. By the 2070s, Venus could become a thriving hub for innovation. Technologies perfected in its extreme conditions will benefit Earth and future off-world settlements. Throughout the timeline, international collaboration will remain central. Partnerships between nations and private entities will ensure that progress continues at a steady and sustainable pace. Each milestone represents a step closer to a permanent human presence on Venus. Through careful planning and collective effort, colonization will transform the dream of living among the clouds into reality. Scaling from floating cities to larger habitats on Venus will require a phased approach, prioritizing stability and resource availability. Expanding infrastructure will transform initial settlements into thriving, interconnected communities. The first step will involve modular expansion. Floating cities will grow by adding interconnected units, allowing habitats to increase capacity without overburdening existing systems. Resource self-sufficiency will drive scalability. Advanced resource harvesting and recycling systems will ensure that larger populations can be supported without relying on imports from Earth. Energy production will need to scale alongside habitat growth. Expanding solar and wind systems, along with advanced energy storage, will meet the demands of larger communities. Transport systems will evolve to connect the growing network of habitats. Airships and drones will ensure efficient movement of people, goods and resources across Venus's skies. Increased automation will streamline operations as habitats scale. Robotic systems will handle maintenance, resource extraction and manufacturing, reducing the strain on human labor. Expanding agricultural systems will sustain larger populations. Vertical farms and hydroponic networks will be scaled up to meet the growing demand for fresh food and bio-based materials. Advanced governance systems will ensure smooth scaling. As populations grow, clear policies and collaborative management structures will maintain harmony and efficiency. Interconnected habitats will allow specialization. Each city can focus on specific industries or research, contributing to a diverse and resilient economy. Larger habitats will incorporate redundant safety systems. Enhanced life support and structural integrity measures will protect against failures, ensuring stability as populations increase. Cultural and recreational spaces will grow with the habitats. Expanded facilities for education, entertainment, and community activities will enrich residents' lives and foster a sense of belonging. Scientific research will accelerate as habitats scale. Larger populations will enable more complex studies of Venus's atmosphere and geology, further advancing humanity's knowledge. Scaling habitats transforms Venus from a pioneering outpost into a sustainable and vibrant society. Each step builds on the last, creating a future where humanity thrives among the clouds. Integration with Earth-based civilization will be vital for the success of Venusian colonies. Establishing strong connections ensures mutual benefits and continuous support between Earth and the floating habitats. Regular communication will maintain ties between the two worlds. Advanced networks will facilitate real-time data exchange, ensuring seamless collaboration in research, governance, and trade. Supply chains will remain critical in the early stages. Transporting specialized tools, scientific equipment, and rare materials from Earth will support habitat development until Venus achieves greater self-sufficiency. Cultural exchange will strengthen the bond between Venus and Earth. Sharing art, literature, and traditions between the two societies will foster unity and mutual understanding. Education systems will integrate knowledge from both worlds. Students on Venus can benefit from Earth-based resources, while Earth institutions will gain insights from Venusian research. Economic integration will create new opportunities. Trade between Venus and Earth can include technologies, data, and resources unique to each location, enhancing both economies. Earth-based governance systems will provide oversight and support. Collaboration with international organizations ensures that Venusian development aligns with shared principles and global goals. Space tourism could bridge the gap between the two worlds. Visitors traveling from Earth to Venus will promote cultural and economic interaction, inspiring further exploration. Scientific partnerships will thrive through integration. Collaborative projects between Venusian researchers and Earth-based institutions will accelerate discoveries in planetary science and beyond. Environmental lessons from Venus will benefit Earth. Understanding climate systems and resource management on Venus could inspire sustainable practices for addressing challenges on our home planet. Crisis response plans will link the two civilizations. Earth-based support can assist Venusian habitats during emergencies, ensuring rapid aid when challenges arise. Integration is not just logistical, it is symbolic. The relationship between Earth and Venus will reflect humanity's ability to expand while staying connected, building a future rooted in shared purpose and collaboration. A thriving Venusian society will embody innovation, resilience, and collaboration. Floating habitats will evolve into vibrant communities where science, culture, and sustainability define daily life. Education will be a cornerstone of this society. Schools and research institutions will nurture curiosity and creativity, fostering the next generation of explorers and problem solvers. Art and culture will flourish in the unique environment. From music inspired by the winds of Venus to literature exploring life in the clouds, creativity will reflect the spirit of discovery. Social systems will prioritize inclusivity and well-being. A sense of community will be fostered through shared activities, cultural exchanges, and a collective vision for the future. Governance will be collaborative and adaptive. Transparent decision-making processes will ensure that the needs of all residents are met, balancing growth with sustainability. Sustainability will guide every aspect of life. Closed-loop systems for air, water, and resources will support a society that thrives without depleting its environment. Intercity trade will strengthen economic ties. Specialized industries in each habitat will work together, creating a dynamic network of commerce and innovation. Recreation and leisure will be integral to life on Venus. Parks, gardens, and entertainment spaces will provide residents with opportunities to relax and connect with nature, even in the clouds. Scientific research will remain central to the society's identity. Ongoing studies of Venus and its atmosphere will inspire new technologies and expand humanity's understanding of the universe. Space exploration will continue as a defining mission. Venusian society will serve as a launchpad for humanity's next steps, contributing to interplanetary exploration and discovery. Global connections will remain strong. Venus will not stand apart, but work in harmony with Earth and other spacefaring civilizations, sharing knowledge and resources. A thriving Venusian society will be more than a settlement. It will be a testament to humanity's ability to adapt, innovate, and flourish in the most extraordinary conditions. It will represent the promise of a future shaped by unity, creativity, and boundless ambition. Venus represents the ultimate test of human ingenuity and determination. In its challenges, we find opportunities to redefine what is possible and to push the boundaries of our capabilities. The vision of thriving cities floating above the clouds is not just about survival. It's about building a new chapter in humanity's story, one filled with innovation, collaboration, and hope. Every step we take toward Venus unites us, reminding us of what we can achieve together. It is a collective journey that celebrates the spirit of exploration and the power of shared ambition. The lessons we learn on Venus will echo across the solar system, guiding our future endeavors and shaping the way we interact with our home planet and beyond. By turning a world of extremes into a beacon of possibility, we demonstrate the resilience and adaptability that define us as a species. Venus becomes a symbol of what can be achieved when imagination meets action. The floating habitats of Venus will stand as monuments to our courage and creativity, inspiring generations to dream boldly and embrace the unknown. Every challenge faced on Venus will lead to new discoveries, not just about the planet, but about ourselves. In solving the impossible, we reveal our greatest strengths. The effort to colonize Venus is a statement of our collective faith in the future, a declaration that even the harshest environments cannot deter our pursuit of knowledge and progress. Venus reminds us that our reach is not limited by the difficulties we face, but by the extent of our vision. With determination, there are no boundaries we cannot overcome. As we look to Venus, we are reminded of our shared humanity. The mission binds us together, transcending borders and uniting us in the common pursuit of something greater than ourselves. The clouds of Venus hold more than scientific mysteries. They hold the promise of a new beginning. They challenge us to think bigger, act braver, and reach further than ever before. Venus is more than a destination. It is a dream, a challenge, and a call to action. It invites us to transform impossibility into reality, to explore not just the skies above, but the infinite potential within us. Thank you for joining us on this journey into the possibilities of colonizing Venus. Throughout this video, we've explored every facet of what it would take to build a human presence in the planet's upper atmosphere, from tackling its extreme conditions to envisioning thriving floating cities. We began by examining Venus's unique challenges, including its scorching surface temperatures, crushing pressures, and corrosive atmosphere. These hurdles demand innovative solutions, but they also provide opportunities for groundbreaking advancements in science and technology. We then explored the concept of floating habitats, where human life could exist in the more temperate layers of Venus's atmosphere. These habitats, filled with breathable air, would offer a lifeline above the planet's inhospitable surface. Energy systems like solar and wind, along with resource extraction from Venus's atmosphere, form the backbone of self-sustaining habitats. By harnessing these resources, we can build a colony that relies on local materials rather than constant resupply from Earth. Collaboration between nations, private companies, and researchers would drive progress, combining expertise and resources to tackle the immense challenges ahead. Partnerships and shared ambitions are key to turning this vision into reality. We also discussed the need for strong governance, ethical frameworks, and sustainability. By preserving Venus's environment and prioritizing equitable resource use, humanity can create a colony that thrives responsibly. Mental health, social systems, and cultural life were highlighted as essential components of a successful colony. Beyond survival, these elements ensure that Venusian society is vibrant and fulfilling. From trade networks and local economies to the integration of Venus with Earth, we explored how this endeavor could benefit humanity as a whole. The technologies, knowledge, and resources developed on Venus will ripple across the globe and beyond. As we imagined the future of a thriving Venusian society, we saw how this mission represents not just a scientific achievement, but a celebration of human creativity, resilience, and unity. Venus challenges us to think beyond limits and act boldly. If you enjoyed this deep dive into colonizing Venus, don't forget to like this video and subscribe to our channel. Check out our other videos for more exciting explorations of the universe and the possibilities that lie ahead. Thank you for watching, and we'll see you in the next adventure.